Hello, 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 hello. I think now I'm audible. Okay, guys. I think now I'm audible. Okay, guys. Thankfully, okay. Thank you, guys. Thank you. Okay, so now I'm audible. So I'll welcome you again, guys. This is our 11th standard, very important chapter named as periodic classification of elements, in which we have to deal with the classification of the elements, and also we'll be dealing with some of the very important periodic properties which are related with the electronic configurations. So we have a class 11 topic where we'll be dealing with historical development of modern periodic table, then we'll deal with modern periodic table itself, periodic properties of all the elements, and then mains and advanced PYQs we'll deal with. Right after this session, I'll also bring a PYQs complete 2002 to 2024 PYQ session where I'll be helping you to solve the questions, and that will be held on probably on the Sunday, this coming Sunday. So that's how our 11th standard this series is working for, and this is all for JEE 2026 people, where we are going to bring all the number of chapters starting from 11th reaching to the 12th. So let's start. Now I'm pretty much audible. So guys, those who haven't liked the session, like the session right now only, okay? And now let me take you to the first part. So what do you think? What comes in your mind when we talk about why are we classification, why are we doing the classifying of element? What's the need? So we need to classify the element because. So there are like till now 118 elements, which is a huge number. So till now 118 elements have been discovered, and out of these 118 elements, let's say if I ask you to learn them. So when we were in 9th standard, and I remember in 9th standard we usually learn atomic number, atomic symbols up to calcium, up to Z, atomic number equals to 20. But that's easy, yaar. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. That's easy because it's just 20 number which we have to learn. What if I ask you that learn all 118 elements? It's very difficult. Not even for me it's possible. But using a proper way and a proper mind map, I can draw all 118 elements. But again, it's not possible to write them in a sequence. So that's why what we need is a proper arrangement, so that we can learn, we can regenerate where is the position of another one and what particular elements are having same number of properties, similar property. So we required a proper classification. So out of these 118 elements, around 93 are metals, 7 are metalloids, and 18 remaining are the non-metals. And in order to learn all of them together in a very systematic way, we require to classify them. So classification is simple meaning arrangement, and arrangement should be done in such a way so that the properties of any element should be repeated after a certain interval. Like starting from lithium, we go from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium. The lithium and sodium are having same property. This kind of arrangement in which the property of one element gets repeated after a certain interval is called as periodic classification. So the definition of periodic classification is the arrangement of elements in such a way where the properties of one element are repeated after a certain interval. That is what we call periodic classification of element, and that's what we have to learn. So this is 418 element what we are doing. So who came first? Okay, how did it start? Who brought this concept of classification? How the classification worked? I remember in 18th century, okay, he is Dobereiner, but Dobereiner mainly came in some 18th of the century, and even beyond that. But if we talk about like around 2200 BC before Christ, and It's a very ancient time. Let me go there. Ancient time. Okay. So there was a scientist, Indian scientist, not a scientist. We call him. He was Mahirshi. Mahirshi Kanad was his name, and Mahirshi Kanad proposed that everything is made up of atoms. Okay, everything is made up of atoms, and atom is the most smallest fundamental unit of any object. So by that time only he brought this concept. Okay, but later on with the time, using the same concept in Dalton came in 18th century, giving this thing that we can classify the elements into two categories, metal and non-metal. And somewhere it is possible to learn all the 18 non-metals, but remembering about 93 metal, it's a hectic task, it's a very chaotic task. So what we do, we will be classifying elements in such a way that Dobereiner gave us. So very first, what should I say, remarkable classification was given by Dobereiner. Let's see what did Dobereiner say. So his name is Dobereiner, and he arranged in the club of three, in a group of three, to the elements, and this group of three is called as triad. So Dobereiner's triad, given in 1817, it's 18th century, okay, I was talking about initial of the 18th century. He said that the atomic, if we keep on placing the elements in increasing order of their atomic mass, and if we pick three of the elements together with increasing order of their atomic mass, so let me give you an idea. So guys, let's say we have three elements, lithium, sodium and potassium. What did he say? That if we increase, if we put them in the increasing order of their atomic mass is increasing, atomic mass increases. So the mass of lithium, we know, let's say I'm writing their atomic mass, and their atomic mass is written by A. A is the atomic masses symbol. It's 7, it's 19, sorry, it's not 19, it's 39. And this is actually 23. So what did he say? That the atomic mass of the central one will be an arithmetic mean of the remaining two. That means it's an average. So let's see, if I find out the atomic mass of sodium, this should come up as 7 plus 39 by 2. And if we do so, it becomes 46 by 2, which is 23. And that made his triad remarkable. He got popular. Okay. Okay, very good, very good. Thank you, everyone. So guys, very good evening to all of you. Might not be responding you and might not be taking your name, but I am continuously watching all of your comment. So whatever the comment comes from your end, whether it's a doubt or not, it's all visible to me. So whatever the doubt will be coming, I'll respond to you by that time. So let's enjoy the class and let me continue from here. So that is what I said, ki Dobereiner gave some of the triad and became very popular by that time. So everybody used to respect triad like this Dobereiner. Wherever Dobereiner goes, everybody shouts, hoots for him. Okay, Dobereiner, Dobereiner, triad, triad. But what actually happened? Dobereiner's triad were applicable only up to limited number of elements. It was not applicable for all the elements. So what actually happened? Let me give you an example. So this is the example. Let's say I have three elements: fluorine, chlorine, bromine. What about their atomic masses? Their atomic masses: fluorine has an atomic mass 19, chlorine has an atomic mass 35.5 U, or molar mass is 35.5 gram per mole, which are the same. Bromine has an atomic mass of 80. Okay, so people asked that Dobereiner, does it follow your triad? He said definitely should follow. Then he went for calculation of the atomic mass of chlorine, and which should be equals to the sum of both two and then divided by 2, which is the arithmetic mean. So 19 plus 80 divided by 2 comes up as 99 by 2, which is 49.5 U. But this is 35.5. Failed. That's where it failed. So that was literally not some very pleasant thing happened with Dobereiner. He got nervous. Everybody disrespected him, said that you're a fraud, and Dobereiner quitted. So these are some examples, guys, where you can find out the Dobereiner's triad will work, but it doesn't work for all the elements. That was the major failure of Dobereiner. I'll move forward and we'll just come to explain the another elements, and then we have failure. So failure is only a few of the triad were possible. Not every element was a part of the triad, and also the triad was applicable up to the lighter elements when the newer elements were discovered. Okay, let's say by that time in 1817, let's suppose that 60 elements out of 118 were discovered. So whenever the next elements discovered out of these 60, it started creating the problems to accommodate them in a set of 3, so that the middle one has an atomic mass of the average of rest 2. So this was not possible. We'll move to the next classification, and before that let's have a question. So we have a question that which of the following triad of atomic masses does not obey Dobereiner's law? So what did Dobereiner say? Dobereiner says that you got to take the average of the remaining 2 first and third. The middle one will be the arithmetic mean of the rest of the 2. So let's see, here we talk about it should be 127 plus 35.5 by 2. How much does it come? So 162.5 by 2 roughly comes up as 81. Okay, I think this can be accepted because roughly this is 81, this is 80, quite nearby. Okay, we'll have the next one. 23. So 39 plus 7 by 2 comes up as 23, which is exactly the similar. So this is also following. What about the C option? Let's go for the C option. So 14 plus 75 divided by 2 will be how much? 89 by 2, which is roughly 89. Okay, 45, 44.5. And I guess this is absolutely different from this term, and that is why not obeyed. Okay, this is where it is not obeyed. So can I see who has submitted me the correct answer? Can I see? So very good, Shabana Shakil, that's good, great of you, very good. Guys, other also can try this question. Bhuvan, Rajkumar, Sigma Male, Devansh Mishra, you people can also attempt the question, and we have plenty of students today with us. Very good, guys. So please keep on increasing your this confidence and try to solve all the questions. So that is the question. C was the correct answer. Okay. So guys, so now, okay, hello Hassan, hello. So guys, what happened after the failure of Dobereiner? Another scientist came with his unique idea of arranging the elements of periodic classification of element, and he said that if you arrange the elements from the lightest one to the higher atomic mass in an order, it happens in such a way, Newlands of octaves, that every eighth element has the same property that was of the first one, and this all thing relates with the Indian musical note, which is sa re ga ma pa. Although there that was a different music they use, and I don't remember it exactly, but they use do, re, ma, pi, I don't know. Anyways, our sa re ga ma pa is good. So sa re ga ma pa da ni sa. So sa means eighth. Okay, again let's see. Sa re ga ma pa da ni sa. This sa is eighth actually. This is eighth. This is 7, and then eighth. This eighth has the same property that was possessed by the first one. So let's see their order. We started from lithium. Okay, so lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then comes sodium, and then these two possess what? Same property. So let's say if I started from boron, aluminum will be the next, beryllium, magnesium will be the next, carbon, 8th will be the silicon, nitrogen, 8th will be the phosphorus, and these two have, these all two, like the 8th one and the first one, these two elements have the similar property. So that was Newlands law of octave, sa re ga ma pa dha ni sa. But what happened actually? So right after discovery, after the discovery of noble gases. So you know what noble gases are? Group 18 elements in modern periodic table. But by then noble gases were discovered quite lately, because noble gases are not very reactive. So you cannot identify them as a, you know, just like iron is present in an oxide, rust is in an oxide. So we can assume, we can think like there is another element which is called as oxygen, and we can think of it. But halogens do not react to each other. That is what halogens are not very much identifiable. Also, they are very much lesser present in the quantity in the atmosphere. So they are present in traces, like very less, 0.01%. This lesser amount of these gases is very difficult to identify. Okay, so that made the discovery of noble gases very lately. But anyways, what happened after the discovery? So earlier we were writing sa, re, ga, ma, pa, dha, ni, sa. Now can you see, like sa, re, ga, ma, pa, dha, ni, sa or sa, where? So this created a gap. So that's where it flopped. The sa re ga ma pa dha ni sa, a set of 7, a set of octaves wasn't working anymore after the discovery of noble gases. So what's the failure? That after the discovery of noble gases, his concept failed everywhere. And also beyond calcium, this repetition was not observed. So he arranged all the existing 57 elements by that time in increasing order of their atomic mass, and found that every 8th element has the similar property that is of first. But this thing didn't work up to beyond calcium. It worked till calcium only. For lighter element only it worked. Okay, guys, hopefully you are understanding. If anyone has any problem, do let me know. I'll resolve your problem right over here in front of you. We have a question on the Newlands law of octaves, that the discovery of which of the following element lead to the failure of Newlands octaves. So which of the element caused the discovery, caused the failure? So failure was caused by the noble gases, no doubt. D. Next. So after his failure, everybody became very sad. People became very sad, everyone, and they thought like nobody is gonna to come to create a periodic table or a periodic classification of the elements so that we can learn all. Then another scientist came. His name is this, which is very big name. He had a name of Alexandra Emily Bayou D. Chencotius. We call him Chencotius. That's a good name. So Chencotius, what did he say? He arranged the elements in the increasing order of atomic mass, and he found that the repetition was taking place, and repetition of the element comes right below it. So like hydrogen is here and lithium is here, then beyond, right next to the lithium, below to the lithium, sodium comes, then beryllium, next to the beryllium, magnesium comes, and that is how a spiral thing was made by him, and it was named as a telluric helix. So this is called as telluric helix, and arranging all the elements in increasing order of their atomic mass, he found that he also found that some of the elements are having a similar repetition of the properties, just like lithium with sodium and potassium, like beryllium showing the same properties with magnesium and calcium. But anyways, it failed because of its complex nature. So here I'm mentioning this part, that why did it fail? Because of its complex nature. It didn't work too much. Okay, then who came the next? Okay, very good, yeah, very good. Thank you, senior scientist, nice. Yeah, we have Lothar Meyer curve. Okay, so this curve was given in 1869. So right after the failure of the 3 major remarkable scientists, now we have the 4th one. The name is Lothar Meyer. So Lothar Meyer brought up a curve which is which looks like a bit difficult, but not that much. There were like 2 axes. One of them is y-axis, that is made up of atomic volume versus atomic number. Atomic volume versus atomic number or mass. Okay, it's atomic mass. So atomic volume versus atomic mass was drawn there, and on the basis of this property only he drew some of the atomic volumes he knew, and he tried to draw a graph, and he found there's a similar pattern, and the pattern says like this. It's a similar pattern for all the peaks what we are getting in a repetition. So guys, you have to take care of this thing, that the maximum of the atomic volume is possessed by what? Alkali metals. Okay, so we will be finding on top rises the alkali metals. So Lothar Meyer plotted a graph between atomic volume and atomic mass, and there are the results of this particular graph, that alkali metals occupy the peak of the curve. And where do the alkaline earth metal come? On the descending part. So there on the descending, decreasing part, what do we have? Alkaline earth metal. Alkaline earth metal. And what about the increasing part? On the ascending part or the increasing part, would we see, chlorine is here, fluorine might be here, bromine. This is where you find the halogens. So that is what it is. And you know what, the transition elements, so this is ascending, descending, and the top. And then we have what do we have? We have transition elements lying down over here, like calcium we have. This is your scandium, titanium, vanadium, chromium, manganese, cobalt, nickel, copper, zinc. But in a club you can see, okay, this is a 3D series, this is a 4D, so I can write it that this part what we are seeing is a 3D series, this is a 4D series, 5D series, but they are in a very narrow range. They are having not so different, not so differentiating, not so very huge a difference between the volumes you can see, and these are transition elements. So this is the classification that was given by Lothar Meyer by knowing the properties called as atomic volumes versus atomic mass. But again it failed because the logic behind the periodicity was not given by him, and also the failure is its complex nature as well. So the many of the physical properties of the element also change in a periodic manner, like melting point, boiling point, density, thermal expansion coefficient, etc. And based on these observations, he proposed that the physical properties of the elements are the periodic function of the atomic mass. This is called as the periodic law. But this periodic law is somewhere it didn't work, and even the upcoming scientists also followed the same periodic law. That is what should I say, like only the one scientist was there who said that this periodic law dependence on the atomic mass is not correct. The major fundamental property is atomic number, not the atomic mass, and that was given by one of the scientists. He will come very soon. We'll let you know. Then guys, we have this became a basis, fundamental for Mendeleev's periodic table. So now I'll bring Mendeleev's. First of all, let's have some question. Lothar Meyer curve was plotted between atomic volume and atomic mass. So volume and mass should be the correct answer. B is the correct answer. Right? Try this question. One more question is here. The question is that the element magnesium belongs to which portion of the Lothar Meyer curve? So magnesium is what? Alkali earth metal. Where does the alkali earth metal situated? Where is it situated? Descending portion. So C should be the correct answer. So guys, now I welcome you to Mendeleev's periodic table, and it was a very what should I say, the most successful and the most appreciable periodic classification was given by him. Now you can look at him, and this is what he used to look like. He was a genius. He always used to wear some glasses and some good aviator. So now I welcome you to this very amazing classification, and look at him, the most cool, the coolest person, the coolest scientist we have, Dmitry Mendeleev. And believe me guys, if you study about Dmitry Mendeleev, you will find so many good and amazing facts about Dmitry Mendeleev. Mendeleev was very much fascinated by the cards. He used to play the cards, and the numbers, and that is what it made him to choose the concept of vertical lines, vertical arrangement called as column, and linear or horizontal lines or rows called as period. That's why he came up with the concept of periods and blocks, no, groups and periods, I guess. So that is what it made the study of these elements even easier. So now I'll take you, first of all, let us understand what did he say. He says that if you increase, like if you arrange the elements in increasing order of their atomic mass, then right after some certain interval, their periodic property will be changed. And the reason behind it is its atomic mass, because he said that the periodic properties and the properties of the elements, let it be physical or chemical, is a function of A, where A is called as the atomic mass of the element. But how, he didn't explain, and that was the biggest failure for him. He didn't explain the proper cause behind the periodicity. No proper reason or explanation was given by him. But yeah, why did he become so popular? So let me give you the idea. He had plenty of elements with him. He know that every element over there exists, and I'm gonna to react. I'm gonna to make every single element react with oxygen and hydrogen to know their valency. So he predicted the valencies by that time, and not just the valency, he also predicted about the so many physical and chemical properties, and he also got to know which chemical properties are similar between the elements. He found lithium is similar to sodium, is similar to potassium, and that's why he used to keep them together. So this kind of periodic table he proposed. That's how its periodic table look like. This is the periodic table. Okay, this is the periodic table of Mendeleev, the periodic table which was proposed by Mendeleev. But don't worry, don't rote learn it. Before that, let's take a look. What did he say? The Mendeleev table was later modified, and then the discovery of inert gas and several other elements also was made. The inert gas were placed in group 0 at last. The vertical groups from 1 to 7 were further divided into subgroups A and B to accommodate more number of elements which are different in the properties. Group 0 was not split further in group 8, and 3 set containing 3 elements were placed. The version of Mendeleev's short periodic table is also, okay, next slide, okay. By that time, when the Mendeleev came in 1871, he arranged 63 elements in increasing order of their atomic masses, where inert gas were not discovered. And let's see, what did he do? This is the periodic table he proposed. I'll again let you know, it's not mandatorily required to rote learn down this periodic table. Even I have the idea, but I don't rote learn this whole table. No, it's not required. But yes, you can do the same for modern periodic table. You can write down every element from the modern periodic table. You can try regenerate it by again and again solving it, so that it can be in your mind every time you think where the position of which element. You can easily classify where does it belong to, what should be the electronic configuration. There are so many things which are connected. So I must basically recommend you to learn down the modern periodic table, but not this one. Just take the idea that 63 elements were arranged in such a way. So you can see that from 0, see this is 0, and on 0 you will only see the helium, neon, argon, krypton, xenon, which are noble gases. From 1st to 7th, they are classified into 2 categories, subset A, subset B. But these A and B elements had no connection with each other. You can check out, like copper being quite inert, doesn't react too much. Potassium, sodium on the other hand are highly reactive. So this is something which is making this whole classification as not very much reliable. And although he gave a very good idea introducing the concept of group and period. So let's suppose you are entering in a library. Okay, you enter in a library, you found a stack, you found a pile of around 1000 books there, and you got to identify one out of them. Is it easy for you? It's very difficult. So what did he do? What if I say that go in the library, go to the 7th row and 14th column, and there your book is. So you'll go to the 7th row, 14th column, you'll find your book over there. So he made the study of elements very easy by introducing the concept of groups and periods. That is the all-time achievement we all accept by Dmitry Mendeleev. So that was the only achievement he got, but not too much of the things. There are the merits of his periodic table. What did he say? That he made study of the properties more systematic and easier by introducing the concept of groups and periods. He also left some of the vacant spaces for the elements which were not discovered by that time, and he assumed that these elements may discover, because an element which is placed right after boron can be named as Eka boron. An element which comes right after the boron is called as Eka boron. The next name of this, modern name of this element was given as scandium. Then he also introduced Eka aluminium. Eka aluminium was later on called as germanium. Nahi yaar, aluminium means gallium. It was gallium. And then came Eka silicon, which was later on called as germanium. So these are the three elements that were actually presumed, that was like assumed by our Dmitry Mendeleev, where he proposed that these elements will be discovered in future, and he named them as Eka boron, Eka aluminum, Eka silicon. So this kind of question may be asked in your exam, that Eka aluminium, what is the correct name of, modern name of the chemical element called Eka aluminium? Gallium, scandium, germanium or titanium? The correct answer will be gallium. So that's what you have to learn. Okay, that was one of the things he did. Another thing is, he also rectified some of the atomic masses. How did he do it? Because as I told you, he used to make the elements reacted with hydrogen and oxygen, knowing about their valency. He always used to think that beryllium has an atomic mass of 4 AMU, not 9. But after discovery of the of its proper valency or its N factor, as what should I say? Mistakenly. Initially, its equivalent mass of its was 4.5, multiplied its valency was 3, and its mass was 13.5 earlier, which is incorrect. Then later on, he found that the properties of beryllium oxide, magnesium oxide, calcium oxide are similar, and he reached to a conclusion that the valency should be 2. That makes its atomic mass as 9, not as 13.5. So 9 was the correct atomic mass, and that's how he rectified the atomic masses for iridium, uranium, gold and platinum. But again, not so much useful data, not a very huge thing to learn about and remember. Simple, take an idea, move forward, that's it, whatever it is needed in modern periodic this is your Dimitri's, Mendeleev's periodic table. So we have demerits. Why did he fail? He failed because he was arranging in an increasing order of the atomic mass, but then he found that mainly of the properties were not matching to each other. So in order to match the properties, he arranged them irregularly. Like take an idea of argon and potassium. So he says that there's sodium, here is potassium, calcium, and then he has argon, then sodium is here, magnesium, and then we have neon here, not neon, here is the argon, and there comes the krypton. But anyways, what I'm trying to explain over here is, so he had to keep all of the noble gases together because they all had the similar properties. Even if I talk about helium, will come up somewhere here. It will be like neon. These all are noble gases and they have similar properties. But the atomic mass, if we talk about the atomic mass of potassium was found to be 39, and this already had an atomic mass of 14. So the question is, why is it coming before potassium? But he had to keep these similar properties containing elements together, which were noble gases, and he had argon with 40 mass, but also placed it before potassium. So that is what it made his theory unbelievable, not very much reliable, and he failed, more or less he failed. So what happens after his failure? He also was not able to explain, let's suppose hydrogen, if we talk about, we have 1H1, we have 1H2, we have 1H3, we call it like protium, we call it deuterium, we call it tritium, and all of three have the same atomic number but different atomic masses, so must be given with different positions as per his concept, as per his theory of creating the periodic table, that all the elements are arranged in increasing order of their atomic mass. What about hydrogen 1, hydrogen 2, hydrogen 3? They also should require different positions, but that was not given by him, so this must have different positions, so that is another failure. And then there was no use of subgroups, there was no significance of subgroup, because the element present in subgroup had weirdly different properties, like copper placed with potassium had no basically similarity, and the position of hydrogen is very uncertain, and where it should be put down, whether it should be first A, where first A is actually alkali metals, or it should be kept in second B, which is halogens. So hydrogen shows a property which is resembling with alkali metals also and halogens also. So in order, because of that confusion, he couldn't pick up a particular position. And the group 8, 3 elements were placed together, which was very much unnecessarily. Look at this periodic table. Can you see iron, cobalt, nickel together, ruhenium, rhodium, palladium together, osmium, iridium, platinum together? What's the use? The question is simply why. He had no clue for that. So that made his study failed. Now you see some of the questions, this kind of question will come, and don't worry guys, there are not so many questions which are going to come from this topic, which till now what we have discovered, because in JEE Main syllabus this topic of early historical development of modern periodic table has been eliminated out, and it's not a part, but in advance it can be asked. But again, in advance it cannot be asked very directly. If the question comes, it will be coming in the terms of some statements wise, and that's why we read it, taking simple idea about everything, and then we'll move forward. That's what we have to do. We are not supposed to learn down everything unnecessarily, because the most important part of this chapter is learning about the modern periodic table and the periodic properties, not with the early historical developments. Now taking you to some questions. What type of oxide will Eka aluminium form? What is Eka aluminium, by the way? Aluminium, gallium. So what does gallium form? Gallium has a valency of 3, so it will form Ga2O3. So Ga2O3 will be C. Correct? C is correct. So anyhow, now we have reached to the modern periodic table. But coming to the modern periodic table, we first have Henry Moseley, the savior of the panel. We have, let's welcome Henry Moseley in the house. Henry Moseley was the person who performed an experiment. He was doing one thing. He bombarded the fast moving electron to different metal target and found basically plotted a graph between the frequency of the emitted radiations versus atomic number. And when he did it, he also found this thing, that let's say if I'm drawing the same graph for different metals with their atomic masses, this is atomic mass, and versus atomic what property was here, this is the nu. What is nu, by the way? Okay, it's root of nu. Nu is the frequency of the frequency of the radiations emitted out. Like that. Okay, so the graph literally came like this. I'm just assuming, might be similar or not be similar. I'm just assuming. But if he tried the same thing using atomic number Z versus the frequency, root of the frequency of the radiation emitted of the X-rays, because whenever fast moving electron beam strikes with a metal target, X-rays are produced, and out of these X-rays, different metal target will produce X-rays of different frequency. So frequency, root of frequency versus the atomic number and atomic masses, the graphs were plotted. He found that a similar graph was observed here in this way, which was a straight line graph. And you know what does it explain, by the way? This explains that Z, which is called as the atomic number, is more fundamental property. It is more fundamental property of elements. Then atomic mass. This clarified the concept which was earlier going on for all the scientists. Everybody used to come there and propose the model in such a way that if you arrange the elements in increasing order of their atomic mass, the periodicity will be observed. But nobody was sure why is this periodicity coming. Nobody gave us the view why is the periodicity coming. But the periodicity was later on explained by Henry Moseley. Henry Moseley said that if you draw a graph between atomic number and root of the nu, it's a straight line graph that represents that somewhere the properties of the elements are connected with, or the periodic properties are connected with its electronic configuration and atomic number, not to the atomic mass. That became a sensational thing by that time and led us to the eventual reaching towards the modern periodic table. This equation, what we see over here, we see that y is directly proportional to x and direct nu is directly proportional to what? Root of nu is directly proportional to what? Z. So that's why we can simply say that root of nu is equals to a into z minus b, which is y is equals to c minus mx kind of graph is here. No, it is like a c minus mx or what? Mx minus c, straight line graph. M is A. Check it out, guys. Very good. They are periodic function of the atomic number, not the atomic mass. And these A and B are some random constants not required by us. None of the question comes on this part. The only thing that we have to take in order to introduce our modern periodic table is this relation. That's it. Now I'll take you to the Henry Moseley's work. This is the Moseley's work. That Moseley's work showed that the proper sequence criteria of the periodic arrangement of an atom is not an atomic mass but its atomic number, and the cause of periodicity is the simply the repetition of the outer shell configuration that you can see. If I talk about lithium, sodium, potassium, rubidium, cesium, for all the one you can find out the electronic configurations as 2s1, 3s1, 4s1, 5s1, 6s1, like that. Got it? So this observation formed the basis for the modern periodic table. So Henry Moseley was the responsible person to brought up the concept of modern periodic law. Then modern periodic law came and modern periodic table became, and this modern periodic table is not a contribution by one scientist, it's a complete contribution from so many scientists. Even our Niels Bohr, Bury was one of the scientists, Alfred Werner also gave some of the contributions, and so many scientists were involved by that time. Okay, Pauli was one of the scientists, Hunt was one of the scientists who involved in it. So there are like a lot of scientists who were involved in making the complete modern periodic table. But yes, the major work and the foundation was kept by Henry Moseley, who proposed us that the periodic function and the periodic properties is because of the atomic number, not because of the atomic masses. Because in atomic number, after a certain interval, the outermost electronic configuration becomes similar, like 3s1, 2s1, 5s1, like 1s1, and that's why they all have the similar properties, physical and chemical. So the physical and chemical properties now a function of periodic, function of their atomic number, not of atomic mass. So what we can say that properties of the element are a function of the atomic number, not atomic mass. This is called as the modern periodic law, MPL. So this is the modern periodic table that you have to learn. Learn it. Using proper mnemonics. But don't ask me because I have my own version, and my version is basically Hindi. Like हेली ना करे सबसे फरियाद, बेटा मांगे कार स्कूटर बाप राजी. So I must say that you must do it by your own rather than depending on me, because I think that learning of this periodic table can happen in either of the way, because I made, believe me, by my time so many teachers were explaining this modern periodic table and they asked me also to learn about the sequences, but I didn't follow them because I had my own version. I also use this thing, lanthanum is here sometimes. This is La is kept here, and in this AC comes here, actinium. So these two are the D block elements only. So ला हफ्ता वारे ओ सिर पटाऊ होगा, ऐसी रफ्तार दवा संग भैया हसमत देश राखसीन. I must say that you should do it by your own. Take your time. I'll connect back. Allow me a minute. I'm bringing water for me, and then we'll continue. So until then, just take an idea how this modern periodic table was made, how to rewrite it, how to rearrange it. Please have an idea. So this is our modern periodic table, guys. So can you teach the Hindi version? This channel is Unacademy JEE English. So not this time, guys, but probably when we'll be having our Hindi channel, we'll definitely teach in Hindi. But I must like to advise everyone. I must want to advise everyone who is watching this session, who will be watching this session later on. Guys, whenever you go for your studies in colleges, for your graduation or post-graduation, majority of the places, majority of the streams that you opt after IIT JEE or JEE Main, JEE Advanced, or like in BTech or BSc, majority of the syllabus is in English. Majority as in everything, I guess, is English. Even in my time of IIT, I completed my 4 years doing the study in mining sector, or where all the books were in English. Every exam comes in English. Everything is in English. I personally want to advise everyone who is watching this lecture that English is a language that we all must adapt, because our syllabus, our need, our basic communication requires English as most of the point of time. Respect Hindi, no Hindi. Hindi is very cultural and very friendly language, but yes, English is very important in order to get connected with the all segments of your academic growth. So I must advise you that English is an important language, and don't just look at English as a language, but also as an important asset of your life. You to treat it. So guys, this is the what should I say, the modern periodic table. As I told you that you have to learn it using your own mnemonics, not gonna to take you to some learning part of this particular list of table what you see. But yes, I can give you a lot of idea, because I have learned it by my own. I have learned it all by my own with my own mnemonics, but I can't use the mnemonics because they are in typical Hindi, or not even in Hindi. They are just meaningless and randomly I have made it. Like, see what I have made it of this. So from here we start the lengthener and actinide from here. So separ and pumsum EU god tab diye ho yaar tum ye bhi lo, and thapayu napayu American CM bank safe essay formed Nolar. My mnemonics are mine only, that I have created by mine. You can check it on Google, wherever you find it the easier way. You can check it with your friends, you can check it with your teachers, wherever you find the easier way. You please adapt it. I can't help you to learn down this periodic table, but yes, the only thing I can help you is to decode this periodic table, understanding this periodic table, what is inside this periodic table. Now I'll take you to the important part of this periodic table. We come to this concept called as first of all, about the periodic table. There are like total 7 horizontal line called as periods, and 18 vertical columns, they are called as groups. Group 1, group 2, group 3, group 4, like that. And if we see that if we move downwards in a group, the principal quantum number increases by 1. Let's take an example. Let's say I'm talking about group number 2. What group 2 members are there? We have beryllium, we have magnesium, calcium, strontium, barium, and radium. Now if you want me to write their electronic configuration, you'll find the electronic configuration will be 2s2, helium 2s2, then it will be neon 3s2, 4s2, 5s2, 6s2, and 7s2. Can you find a difference between 2, 3, 4, 5, 6, 7? It's an increment of one number when you go from top to the bottom, increases by 1. Next is, so according to the IUPAC, there were like different numbering given. This is where it is written. So can I use my own? Yeah, I can do it. So how is it given? How these numbers are given? Let me give you an idea. So how these numbers are used. We have first, which is also called as first A. We call this thing as second A. We don't call it third A, we call it third B, fourth B, fifth B, sixth B, seventh B. We call 8, 9, and 10 together as 8th. Okay, 8th or 8th B. And then we have 11 and 12. This is called as 11 is called as first B, 12th is called as second B, and then second A, then it comes the third A, fourth A, fifth A, sixth A, seventh A, and then it is the group 0, and you can also call it 8th A or group 0. So guys, this number what I'm writing is not some random number. This number has been given by Dmitry Mendeleev while he was proposing his own periodic table. Then he proposed these numbers: first A, second A, third A, fourth A, fifth A, sixth A, seventh A, eighth A, or 0, and then third B is fourth B, fifth B. This is the number that you have to learn. And again, this number is pretty simple, that 7th B is 7th period, 7th group, 13th is your third A. So this is something which is very amazing, okay? And question may come directly on this number, that how many members are there, or let's say the general activity configuration present for 13th, like it will not say directly that 13th group, it will say you third A. So you have to predict by your own, okay? Then we have 14 elements of both 6th and 7th periods are called as lanthanide and actinide. So 14 elements which are both of 6th and 7th periods are called as lanthanides and actinides respectively, which are separately placed over here. So I can give you this idea that this is your lanthanum, by the way, La, and this is actually hafnium, and from there it starts, okay? So this atomic number is 57, this is 58. You might be expecting that from 56, 57, 58 it should be, but it is not 58. Sorry, my bad. Why did I write it 58? This is not 58, this is 89. This one is 89. I was expecting that this should be 90, but this is not 90. There's a gap of 14 elements. These 14, see, 89, 90, 91, 92, 93, like that till 103. This comes 104, and this comes 72. So this is what we have to take in our mind, that there are two different kind of series and block called as F block, for which these 28 elements have been kept separate from the periodic table to accommodate. Otherwise, this thing will not be accommodated over here in this way. Then we have, I think that's it. So if we talk about the metals, there are like total 93 metals present out of this 118. So around 78% of the elements are metals, and these all metals are generally solid at room temperature, except one metal which is mercury, that remains liquid at the room temperature. Melting point and boiling points of metals are generally high, but gallium, cesium, and even mercury, these three have very lesser melting point. We say that if we keep the gallium in our palm like this, it will get melted because its melting point is just higher than the room temperature, just higher as in it's like 303. So 303 minus 298 will be 5 degrees Celsius. It's like 30 degrees Celsius. So 30 degrees Celsius can be maintained even by keeping something like this, giving it the body temperature and the heat. It can come down to the liquid state. Then these all are good conductors of electricity and heat, and they are malleable and ductile. You can beat them to make the sheets, called as malleability. You can draw wire out of them. This is called as ductility. That's a 10th class topic that you are right now learning from me. We have non-metals here. Non-metals, what non-metals are? So non-metals are located at mostly in the P block, and all the non-metals are majorly gases and solids. Only non-metal which is liquid in state is the bromine. So it's an important part, and that's why I'm star marking this thing. Also a few of them like carbon, sulfur, phosphorus, they exist in solid form, and they have low melting and boiling point, like boron and carbon in their crystalline allotropic form. They have the higher melting points, like diamond, graphite, they have a higher melting point. But apart from these all, oxygen, nitrogen, fluorine, halogens, and even noble gases, they all are gases, and they have very less melting and boiling point. They are very poor conductor of heat and electricity, and they are brittle in nature. If you beat them with some application of force, they will shatter down. I think this is absolutely clear to all of you. Okay guys, so keep on liking the session. Okay, those who are watching right now, please like the session. That's more important part of this chapter, that we have to keep on liking the session. Okay, we have metalloids. So metalloids are something which has similar properties. So there are like 7 metalloids. 7 metalloids are there, and how did I remember them? शिव भोले तेरी ऐसी पूजा के sab jiye. Now you might be wondering what I'm saying, but believe me guys, I learned all these 7 like this. This is your silicon, boron, tellurium, arsenic, polonium, antimony and germanium, and I learned them when my teacher taught me once that Shiv Bhole, the Lord Shiva, we have to worship Lord Shiva. Shiv Bhole तेरी ऐसी पूजा सब जिए जिए. Okay, again bit of Hindi, but yeah, mixed of things. So they have quite properties which are similar to metal as well as non-metal. That's why they are kept under a different category called as metalloids. They are not typical metals. They are not typical non-metals. They are not very excellent conductors. They are not very bad conductors. They are like good conductors of heat, electricity, and they are semiconductors. Silicon as a semiconductor, we have seen so many applications in nowadays device like electronic devices and gadgets. They have microchips which are made up of silicon. So that's the use of metalloids we have, and that's a simple idea we took about how many of them are there, what's their name, and what's the element. Now, on the basis of the something that we have right now discussed about the modern periodic table, we have some questions, and I want every one of you to participate in this question. Element which are generally bad conductor. Oh my God, bad conductor. Who are bad conductors? Actually, they are non-metals. Okay, so let me take the idea. They are nothing non-metals. Okay, then the non-metals which are bad conductor of heat and electricity are found in which side of the periodic table? So basically, non-metals are where do they exist? They exist in P block. P block, the rightmost block, which is right side. The leftmost side is made up of S block. All of them are mostly of metals. The D and F block at the mid of this periodic table, they all are metals and they are very excellent conductor of electricity. The rightmost part is made up of some non-metals, metals and metalloids, but majority of them are non-metals, and that makes this department having lesser or poor conduction of the electricity and heat. There comes the right portion, P block. Now I'll give you a very amazing trick to know how did the names of these elements came. So before the discovery of the newer elements like organozone 118, okay, flavoranium, livermonium, these elements are recently being discovered. Before their discovery, they were written down as UUP, UUH, UUC, UNN. What is the meaning of this UNN, UUP, and how are they named? So there is a simple thing that I'll let you know. So let us suppose the number is 118. Let's see, the number, atomic number is 118, and we all know Z is equals to 118 for the most recently discovered element, that is organozone. But before writing it as an organozone, it was written down as UUO. How? So guys, this one means un, the another means un, this is oct, and we have to add em at the end, em. So unoctium is the number of this. What is the symbol? What kind of symbol are we going to use for this element? This will become UUO. Any doubt, anyone? Please let me know. So that's how easy these namings are. That's how easy these namings are. Hopefully this is absolutely clear to all of you, whoever is watching it and who will be watching later on. This concept is highly easy. So let it be any kind of number is there. Let's say I'm saying that it's a 200 number. Let's say okay, it's a 200. So 2 means by, O means nil, by nil, nil em, by nil nilium, and it will become, the symbol abbreviation will be BNN. So the only thing that you got to learn about these things: 0, nil, un, bi, tri, quad, pent, hex, sept. We don't use hept. That hept is used in organic chemistry. We use here sept and oct and n. So let it be any number that you can pick. Let it be any number. You can give its name as well as you can also use its abbreviation as atomic symbol. So let's say the element is 100 and 6. So what are we going to use? 1 for un, 0 stands for unnil, 6 will become hex, and then we'll put em. Unnil hexium. How easy is this? The symbol will be unnil hexium, UNH. Got it, everyone? Whenever you find there are two things, one of them is there's a repetition of the similar thing, then it will be like bi plus em. If bi is written, em is there, then it will become bm. If tri is written somewhere and then em is written, it will become trium. Okay, that's what we have to follow. Rest everything is very easy. Now we'll go to some questions. There's a question that the elements silicon and germanium are what? Metalloids, as I told you. Shiv bhole teri aisi puja sab jiye. Atomic number of which of the following is unnilenium? See, unnil, so unnilenium. Un stands for 1, nil stands for 0, enium means 9. 109 is one we are talking about. A is the correct answer. The IUPAC naming for the element with atomic number 119 will be what? IUPAC symbol, we have to take it. First of all, I'll give it the name. It will be unalenium. Unalenium. So this will unalenium. UUE. Where can you find UUE? B. Name this correct matching and all, that you can do it by your own. If not, take my help. I can also lead you. It's an all application of periodic table itself. None other than that is used. Unnilenium. Okay, unnilenium. What is it, by the way? Unnilenium. Okay, I'll write down their number, by the way. Unnilenium. Onion means 101. Unniltrium 103. Unnilhexium 106. What is it? Ananium 111. So we have to match them. Okay, this is Mendeleevium. Formed Nolar. Okay, I'll basically give you the name. American Bank Safe Essay formed Nolar. So LR is 103. Are you sure? 103. So if it is 103 FMMD, this is actually the atomic number is 101. I know because I can relate it. So incorrect match you have to give it. Laurentium. Laurentium is LR, no LR. Laurentium, yes. Lutetium is LU. So where did you see the Laurentium? Formed Nolar, LR. Formed Nolar 103. Then Seaborgium, SG, Sang Bhaiya Hasmat. So SC starts from AC. Actinium has an atomic number of 89. So AC, Lothar, then Lothar comes to 104. 4, Daba, Deborgium 5, Seaborgium 106. Seaborgium has 106. This is also correct. Probably this is the correct answer. Darmstadium, which is your Acirta Daba Deborgium Seaborgium Stadium. This is DS. This is DS. Okay. So see, this starts from C. Actinium, Rutherfordium. Rutherfordium comes up as 104. So Rutherfordium, Star Tapa Sang. Here has Desh. So 7th. So 4, 5, 6, 7, 8, 9, 10. This is 110. Oh my god, this is the one which is incorrect. So the correct answer should be D. D4 is the correct answer, because the given one is 111, the atomic number is 110. You might be wondering like, how am I doing it by my own? But believe me guys, this is the hack actually about this whole chapter. You only need to learn down this whole modern periodic table. If you are pretty much able to learn down this modern periodic table, believe me, everything will become highly easy to you. Okay, so you just do one thing, just learn down this periodic table and try to take some mnemonics, and you also must know how the atomic numbers are there. And the most important part is that D and F block, especially if we talk about the F block, lanthanides and actinide. So lanthanide starts right now lanthanum, which has an atomic number of 57. So from 58 to 71, 58 to 71, total 14 elements are of lanthanides, and lanthanide ends at lutetium. Then comes your hafnium. So hafnium has an atomic number of 72. So like that, you have to remember, and that will help you to bring out all the atomic numbers by your own. Okay. Okay, biomolecular chapter. What is this biomolecular chapter? Okay, biomolecules I'll bring very soon. It seems like I've taken one session on biomolecule, and even if not, then I'll bring it very soon. Don't worry. Probably on Sunday I can arrange a chapter on biomolecule. Not a big deal to me. We have blocks in modern periodic table, everyone. We have some blocks in modern periodic table. What this block mean? So we have P block, D block, F block, and all. That is called as S block. The most active metals, because they have because we'll come to know about that also, they have lesser number of electrons in their outermost, can be easily lost, and can give it an electropositive character or metallic character. They are metals, typical metals. They are typical metals too. They are lying at the center of the periodic table. These are typical metals too, and these contain mixed of metal, non-metal, and metalloid. So that's what our differentiation is. If we talk about the S block elements, all these block elements, they have an electronic configuration 1, 2, 2, NS1. NS1 is for alkali metals. What alkali metals are? लीना करे रब से फरियाद, up to francium. And then we have another NS2. That NS2 is for alkaline earth metals. So for alkaline earth metals you have beta mange car scooter baap razi. So like that you can do. Sir, note for amines and hydrocarbon chapter. Okay, for hydrocarbon and amines, if you haven't got the notes, I'll provide them, but I'll discuss it from my team also, that why didn't they provide the notes. Okay, that's it, I guess. Okay, right after this, I'll also explain one very important part of this chapter called as magic number, and that will literally create a magic over here. Okay, it will definitely create a magic. Anyways, until then, we'll take the properties. They are all electropositive in nature. Group 1 and group 2, they all are active. They lie on the extreme left of the periodic table. Then we have P block right on the extreme right, and their general configuration. Don't use this configuration. Use my configuration. My configuration says that it is NS2, then N-2, F14, N-1, D10, and then NP126. Right, guys? Okay, so that's an electronic configuration we should take. You might be wondering, how am I taking this? Let's say I'm talking about group 13. What members are there in group 13? Boron, aluminium, gallium, indium, thallium, and then come NH. So out of these all, and I can also explain you the atomic numbers. Boron has an atomic number of 5 plus 8, 13, 13 plus 18, 31, 31 plus 18, 18, 49 plus 32, and 18 plus 32. That's it. So these are the atomic number. So how should I write down their electronic configuration? So configuration is NS2, like that only I'll use. Boron. So before boron there comes helium. So we can write simply helium. Helium ends to 1s2. Then it will come 2s2. But we do not have any 2 minus 0f is not exists. 1d doesn't exist. So we'll simply write 2s and 2p. So we'll make it 2p1. Similarly, if I ask you for aluminium, the next noble gas to helium will be neon. Right after finishing the second period up to neon, we have third period, so this will be 3s2. Then again 3 minus 2 doesn't exist, 3 minus 1 d doesn't exist, we will simply write it 3p1. Now coming to gallium, we have argon 4s2, but you know what, 4 minus 2f doesn't exist, but 4 minus 1d does, so we'll write it 3d10, and then I'll write it 4p1. Then we have indium, so helium, neon, argon, krypton, xenon, I forgot some, helium, neon, krypton, helium, neon, argon, krypton, xenon, radon. No, it's fine, radon, and then comes organizon. So krypton, we will write 5s2. 5 minus 2f doesn't exist, 3f, but 5 minus 1d does, so I'll write it. So it is 4d10 and a 5p1. Similarly, 6s2 is there, 6 minus 2 is 4f, so 4f14. 6 minus 1 is 5d, so 5d10, and then comes 6p1. This is also the same. 7s2, 7 minus 2f, so 5f14, 7 minus 1, 6d10, and 7p1. That is how you can write down the electronic configurations. So if you know this general electronic configuration, ns2, n minus 2, f1 to 14, sorry, not 1 to 14, just simply fully filled 14, n minus 1 d10, and then np 1 to 6 you can fill in. I'll also give you some of the very important hints and some of the very important techniques to find out the electronic configuration, okay? But until then, please make sure that you are correctly doing it, following me. That will be highly helpful. So together, S block and P block, we call them representative element, but these representative elements do not contain noble gases. Star mark. Then include some metals. All it has metal, non-metal, and metalloid, everything in it. They lie on the extreme right, and groups are 13 to 18. There are a total of 6 groups are there. We have D and F block. D block elements, actually majorly D block elements are called as transition element because they come as a transition, as a bridge between S and P. There's one reason. There's another reason is we know that all the D block elements, they have unpaired electrons in their noble or ground state, or in their excited state, they have unpaired electron. That presence of unpaired electron makes them to do transition. That electron keeps on transitioning. Okay, there is a term called as DD transition that will come to know in 12th standard in coordination compound. But again, we know that it does transition, and that's why we name them transition elements, because of the presence of their unpaired electrons in their ground state or in their excited state. So anyone, if you want to ask me that what groups are there from group 3 to 12, they constitute in the modern periodic table, and then their general configuration will be n minus 10, n minus 1 d 1 to 10, ns 1 to 2, except palladium and has a exceptional one, krypton pd10, 4d10, 5s0. Please mind these electronic configurations are very important, and especially learn it for palladium. They all are metals and they produce colored ion because of the unpaired electron, which does the transition in the visible line of the visible line, and then it's visible to us as a fascinating color. First series is called as 3D series from scandium to zinc. Second is called as 4D series yttrium to cadmium. Third is called as 5D series from lanthanum, hafnium, and mercury. And then 4 transition series comes from actinium, rutherfordium, and selenium. So there comes, these are called as transition atal, except the group 12. Group 12 elements are called as pseudo transition element. They are called as why are we calling them pseudo, not transition? Because they have no unpaired electron in both of the ways, either in their ground state or in their excited state, like Zn2 positive. It has a complete electronic configuration of 3d10, fully filled 3d10. No unpaired electron is there. That makes it zinc as a pseudo transition element. Guys, got it? Yes, absolutely. Now I'll take you to the next elements called as F block element. They also have very difficult electronic configuration, not very easy, not very convenient. The electronic configuration is, general electronic configuration is n minus 2, F14, n minus 1 d0 to 1, and then have ns2. So it's not that simple, but you can use it like this: ns2, then n minus 1, d comes from 0 to 1. Somewhere mainly it is 1, but somewhere it is like 0 also. So in order to give it an extra stability to the electronic configuration, sometimes it becomes 0 also. And then comes ns2, n minus 2, f 1 to 14. And believe me, lanthanide and actinide are not F block elements. We people are sometimes in a very huge confusion. And every time I see people in this confusion, they say that lanthanide and actinides. Okay, I forgot it. Now I'll take the words back and we'll repeat. So this is the general electronic configuration for F block elements. And don't fall in this confusion that lanthanum and actinium are also F block elements. They absolutely are not. The lanthanum, actinium, both of them belong to D block only. But the elements right after them are called as lanthanide and actinide respectively, which are your F block element. So now I'll take you what's the fine. So we have lanthanides from 58 to lutetium 71 and 90 to 103, and just learn it. Because why I'm calling it? Because their group number is 3 and their period is 6th and 7th. So these are very important to identify their respective numbers, and it's very important part of this chapter. And also they are called as, because they lie between the transition element, they are called as inner transition element. They all are metals, and within their series the properties of the elements are quite similar. Majorly of the actinides are radioactive, and they all after uranium are called as transuranic elements. Then they all belong to group 3 and placed separately at the bottom of the periodic table that we saw. Okay, next, some questions. What is this configuration used for? So whenever we write the configuration as ns2, or somewhere it becomes ns122 and n minus 1 d 1 to 10. This is actually D block. D block element is there. The general electronic configuration for D. Oh. Now I'll take you to the most important part of this chapter called as magic number. Whoever is watching this video, you all must know the magic numbers. Magic number will definitely help you to identify the atomic number of whatever element is there inside the modern periodic table. Out of all 118 elements, you can write down the atomic number just by simply thinking in this way, magic number. But yes, the magic number differs for the different block. So first I'll do it for S block. For S block, what elements are there in S block? We have hydrogen. Helena करे रब से फरियाद, and we have beta मांगे car scooter. No, from here it's our beta मांगे car scooter बाप राजी. So what are their atomic number? Basically from their atomic number, the changes from their atomic numbers are called as the magic numbers. Okay, the changes you'll be getting from their atomic numbers is called as the magic numbers. And it's very easy, by the way. The general magic numbers are 2, 8, 8, 18, 18, 4, 32, like that. So this is actually 2, 8, 8, 18, 18, 32. This is the sequence. And there we have 8, 8, 18, 18, 32. These are the magic numbers. So talking about the atomic number, hydrogen 1, 1 plus 2, 3 plus 8, 11 plus 8, 19 plus 18, 31, 31 plus 18, 49, 49 plus 32. Okay, let me see if I'm going correct or not. 37, sorry, by the way, 37. Then 37 plus 18, 55. And then 55 plus 32 will become 87. Beryllium, atomic number is right after lithium, it will become 4. 4 plus 8, 12. 12 plus 8, 20. 20 plus 8, 38. 38 plus 18, 56. And 56 plus 32 is 88. So guys, these number whatever are written in the white font are called as the magic numbers, and they are very important to identify the atomic number of all the elements placed in a group. So for different blocks, we have different set of magic number that we must know in order to get the atomic number for all the elements possible. These are magic numbers. So now let's say for P block we want to find out the magic number. So P block. So P block, the magic numbers will vary. So how? I'll tell you. So let's say if I'll to start it from group 13, group 14, group 15, 16, 17, and then we'll come to group number 18, which is called as the normal gas. So group 13 elements are boron, aluminium, gallium, indium, thallium, NH. Group 14 are carbon, nitrogen, अरे नहीं यार, carbon, silicon, germanium, tin, lead, Fl. Group 18 are this starts from here: helium, neon, argon, krypton, xenon, radon, oganesson. So that's how we have to write down. And there like if we talk about their numbers, so they are 8, they start from 8 actually, 8, 8, 18. So let's see if I have done it correctly or not. This is 8, 18, 18, 32, 32, and there we have starting from 8, 8, 18, 18, 32, 32, and there also we have the same 8, 18, 18, 32, 32. These white fonts are the magic numbers, and they help you to identify the atomic number. How? This boron has an atomic number of 5. 5 plus 8, 13. 13 plus 18, 31 plus 18, 49 plus 32, 71. No, 71 no, 81 I guess. 71 will be a lutetium I guess. 81 plus 32 will be 111. I think 113. Yes. Then again this will be 6 is the atomic number. 6 plus 8, 14. 14 plus 18, 32. 32 plus 18, 50. 50 plus 32 will become 82. 82 plus 32 will become 114. So that's how you can identify the atomic numbers. Okay. There also we can find it out. So this is 2 plus 8, 10 plus 8, 18 plus 18, 36 plus 18, 54 plus 32 is 86 plus 32 is 118. So guys, the number you see on the board which is in white font, they all are called as magic numbers, and they are very important in order to identify the atomic number of all the elements they are placed in a group. So it's an important number that gives you an idea about the electronic configuration and atomic number for the elements placed in a group. They are magic numbers. Fine, Vijaya. Welcome, Vijaya. Let's say if we talk about the magic numbers for D block. We also have a member of D block. D block as in like this is called as 3D series. We have 4D series, 5D series, 6D series. Okay, and this is your period 4, period 5, period 6, period 7. What elements are there? I'll write them. So this is scandium, titanium, vanadium, chromium, manganese, ferrum, cobalt. Okay, I must not write too many. So this is scandium, this is titanium, and it is vanadium, chromium, manganese, ferrum, cobalt, nickel, copper, zinc. We have scandium, we have ytterium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, cadmium here. 5D series lanthanum, hafnium, tungsten, rhenium, rhodium. So, but how? Mercury. Then actinium, rutherfordium, deborgium, seborgium, and at last we'll be having Ce, Cn. So these are actually 3D, 4D, 5D series and all. But again, white font will give you the idea about the magic number. So scandium, this magic number works like this, guys. This has a difference of 18. This has a difference of 18. This has a difference of 32. But here, on the very next, you have 18, and then simply comes 32, because there we have the lanthanides in between, and there we have the actinides in between. Okay, star and double star, and there also we have 32, and the same thing works over here also. A difference of 18, a difference of 32, and another difference of 32. Let me write their their atomic numbers as well using this data. Scandium has an atomic number of 21. So 21 plus 18, 39. 39 plus 18, 57. 57 plus 32, 89. Now we are expecting it that this is 21, this should be 22. Of course it should be 22. 39, it should be 40. Yes, of course it is 40, but no, this is not 58. Rather than 58, this is 72. So where did this 58 to 71 14 elements go? These 14 elements are actually, these are your lanthanides. So I can mention this part somewhere, that the star is actually lanthanides, F block elements, lanthanides, from Z is equals to 58 to 71, and the double stars are your actinides. For Z, their Z is 90 to 103, and they all both belongs to the F block. Mark this. So this is how you have to do it. Now again you add 72 plus this will 104. After 32 we will add it. And zinc also. How zinc has 30. 30 plus 18, 48. 48 plus 32, 80. And then 80 plus 32 is 112. So that's how you can write the atomic number, electronic configuration, any of the property that you want to write for all the elements, if you know about the magic number, because magic number is an important thing that you got to know. Rest you can do it by your own. F block doesn't have any magic number, because in F block the only magic number will be working is 32. There's a difference of 32, by the way. Well, they all belong to the same group. That's why we don't say about any magic number there. Okay, so magic number, instead of magic number we use this data, which is very important. This data is important. Now see some questions. Let's see some questions. The atomic number of silver is 47, and in the same group the atomic number of elements placed above and below silver will be what? So I told you, let's say this is silver. What we are talking it about is group number. It's a D block, by the way, so no doubt it's a D block, and D block, and it's a group number. Group number 11 we are talking about. So we have silver, So you know the magic numbers, guys. I told you the magic numbers are 18. What was it? From copper to silver will be 18, and then will become 32. So these are what? These two are the magic numbers which are helping us. I told you that magic numbers are helpful. These are the magic numbers. So using this magic number, you can identify the atomic number. This is 47. So decreasing, this will give you copper at 29, and copper, silver, and then gold will be your 32, 79. Check out. Correct answer 79, 29. C. No, 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 no. The set that contains atomic number of only transition element, of only transition. You apply your mind, you can do it by your own also. And don't worry, guys, I'll bring a session from 2002 to 2025. All JEE Main and advanced problems, not advanced, they are only JEE Main right now we are bringing to all of you, and there will be discussing all the concept we'll discuss there. All the questions practicing will be done by on there by very soon. Okay, so the set that contains an atomic number of only transition element is the set that contains atomic number of only transition element is only transition element. Can you see where? Only transition 21, 25, 42, 72. 72 cannot be taken, or we can take it. I think this is correct. This 9 cannot be a part. There we see 37 cannot be a part. 21, 53, 64 cannot be a part. Seems like B is correct. A question came in JEE Main 2020 upon the same concept regarding group number, block and all something, I guess. So the element with atomic number 101 and 104 belong to where? I told you once that that from 90 to 103 they all are actinides. So this 101 is what? Formed no LAR. This is your Mendeleevium MD with an atomic number of 101. And what about 104? So right after AC Rutherfordium. This is the Rutherfordium 104. I know about everything, yeah, because I have gone through this periodic table so many times. So what kind of group number is there? And they all actinides have a group number of group 3 they belong. So this is actinide, and this belongs to 3, 4. 4 will be the group of Rutherfordium. So group 4 and actinide. C is the correct answer. C is the correct answer. You can check it out. Then there's a general discussion about what group number means. Group 1 alkali metal. These are the alkali metal. Alkaline earth metal group 2. Coinage metal is group 11. Meanwhile, whatever the group is there, they might not be having very remarkable name. That's why we are not bringing them over here. Group 13 is called as boron family, carbon family, nitrogen, chalcogen, halogen, and noble gases. This some names are there, and their exact significance will be learning when we'll be dealing with the block-wise strategies. Okay, block-wise study when we'll be conducting. Nitrogens, they are some sniffing gases. Then they can cause choking, like nitrogen, phosphorus, and their hydride, especially phosphine, ammonia, like that. Chalcogens are chalk means they are ore forming substances. Majority of the minerals are found in the form of oxide and sulfide. So oxygen sulfur belongs to chalcogen. Halogens, you all know, salt forming like AgCl, or salts like in halogen. Okay, sodium chloride, chlorine, fluorine, bromine, iodine. And noble gases, you all know, which do not react with anyone and they keep on they keep inert. And these are helium, neon, argon, krypton, xenon, radon. Now I'll try to explain you one more important part of this chapter called as knowing about the group period and its block by simply knowing the electronic configuration. If you know the electronic configuration, you can identify an electronic configuration. I taught you in the atomic structure chapter. So we'll take the application, we'll know how do you identify. So first of all, just go with the highest number, period number, highest principal quantum number, except the case of palladium. Only the case of palladium. Palladium, I gave you an example few time back. There only we were discussing about it. Anyways, palladium, we all know where does it belong to, but yeah, all of them will follow this. Highest principal quantum number is the periodic number. Group number is separately given. Block is the valence electron goes to which shell. So that's what also you can find out. And then knowing about the blocks. So total number of valence shell electron present in the S subshell is called as the S block. S1 means first, S2 means second. This is group number 1 and 2. For P block, the total number of valence electrons including S and P, and then you add 10 in that, because this 10 is because of the meanwhile the 10 groups are there of D block. Or you can also do simply number of electrons in P subshell plus 12. That will also give you the same answer. If we talk about the D, then NS and ND, you got to add NS and N minus 1D. And for F, all belongs to the third group only, that I told you exactly a second back. Now allow me a second, everyone, just read it out and I'll connect you back, okay? Then I'll connect you back. So, well, somebody was asking me that where is the teacher? I told you guys that please have a look on whatever written over here. I'll come back in a moment and will join you shortly. I told you by that time only, okay? But don't worry. Now I'll give you one example on the whatever it's been written over here and what you have gone through. I'll give you one example, a very beautiful example. Everybody please have a look. So let us suppose our atom is chromium with an atomic number of 24, and we all know how to write its electronic configuration in its ground state. Electronic configuration will be argon 4s2 and 3d4, or you can also write it 4s5 and 3d1. Let's say 4s1 3d5. Okay, 24 electrons have been filled, argon with 18, and these 6 electrons combinedly 24 electrons are there. The question was quite simple, that what will be the block, period and group. So how do you identify that? First of all, what is the highest number can you see in this whole periodic, in this whole electronic configuration? This is the highest principal quantum number. So that becomes its period number. So what period does it belong to? It's in fourth period. Fourth period element is chromium. Now we'll be asking me what is the block. The block is something that last electron goes to. Where does the last electron goes? This is where the last electron goes to. So the block will become automatically where it goes to D. And the third part is, what is the third part? Block, period and then group. Which group is this? Which group are we having chromium into? So for group we have number of electrons in ns, ns plus n minus 1 d electrons. How many ns are there? 1 plus 5 equals to 6th group. That's how we do. So just have a proper example, have a proper set of practice. How do we approach these questions and how to identify period, block and group. Let's see one more question. The last element of P block in 6th period is represented. 6th period? Okay. Outermost electronic configurations. To me it's very easy, but I want you people to understand. Last element of P block. So do you know what the last element meaning? Last element means definitely we are talking about the noble gases. Noble gas, and that is group 18 by the way we have to talk about, okay? So helium, neon, argon, krypton, xenon, radon, oganesson. So this is the element this question is asking about, radon. Because this is what? Second period, third period, fourth period, 5th period, 6th period. What's I'm doing here? This is first period, second period, third period, fourth period, 5th period and 6th period. So this is 7th period. The 6th period was we were talking about. So in 6th period the last, okay, electronic configuration is being asked. No problem, I'll do it. But before that, I told you once that use ns2, n minus 2, f14, n minus 1, d10 and np6. So n is 6p6. So can you identify this configuration somewhere? So it's 4f14, 5d10, 6s2, 6p4. Correct answer will be. It's just a way of representation. Believe me, the best way of representation is this, what we are bringing over here, ns2, n minus 2f, because this is the order of energy that we have to fill in. This is the order what we have to fill. This is actually n plus l rule that we have followed in second chapter while writing the electronic configuration of elements. Very easy one. Taking you to the next question, we have Z is equals to 114 has been discovered recently. Okay, so it will belong to which family? You know, it's very easy again. So 114, you know what? 114, 115, 116 and 118, and we all know that what 118 belongs to. This 118 belongs to group number 18. So this will be group number, okay, I forgot to write 17, sorry. 17 and 118. So this is group number, this is group number 18, group number 17, group number 16, group number 15, and then group number 14. So what element are we talking about right now? This is our element what we are talking about. This is 114. There we go. And I can identify the elements also that so these all are 114. So this is actually 7th period elements are there. 7th period. So 7th period 114 will be FL. We have this is Moscovium. We have oxygen, sulfur, selenium, polonium, livermonium. So LV. Group 17 we have tennessine. Okay, iodine, fluorine, bromine, iodine. I forgot. TS tennessine, and then this is OG. So anyways, we are talking about this flavoranium. This is 114 is the atomic number. So electronic configuration is very simple. I told you once, if hope you remember it, that 7s2, 7 minus 2f 14, 7 minus 1 d10, and 7p2. 7p2. So correct answer should be 7p2. 7s2 This is the correct answer. I think carbon family is the correct answer. So you must need to know how to identify. Okay, we have to know just to identify that where the element belongs to and what electronic configuration do we need to write. We have Roman with us. Roman is asking me some question that where is Kailash Sharma sir? Roman, I'm sorry yaar, but I have no idea, and like me and Kailash sir haven't spoken for a long time, and nowadays I stay in Bangalore. I guess he stays in Kota. Haven't spoken to him, but anyways I'll communicate with him and we'll let you know. I don't know where, but somewhere we can connect. The elements with the electronic with the atomic number 118 is, we all know it is organizone and it belongs to noble gases. Okay, so most easy question probably of the day. The element with atomic number 36 belongs to. So I told you, whenever the atomic number is given to you, just try to apply the concept in such a way. The element with atomic number I think this is krypton. I know about krypton. How do I know about it? Helium, neon, argon, krypton, and like that. So the atomic number we all know. Do you remember the magic number I told you? 8, 8, 18, 18, 32, 32, like that. So helium is 2, 2 plus 8, 10, 10 plus 8, 18, 18 plus 18, 36. 36 is krypton. What is the correct answer? Which block is there? P block, A. Next. So next is another question that I would like to give you as a homework. We don't have plenty of time. We'll go, we will move forward with some other questions. So next is merits of the modern periodic table. What is the benefit of modern periodic table? The major benefit is the very, you know what, a very beautiful arrangement, a very convenient arrangement we got by introducing the concept of horizontal rows as period and vertical lines as vertical columns as groups. So introducing the concept of group and period made the study of each and every element very easy. So this is where we got it. The table is based on more fundamental property called as atomic number. We had the proper explanation behind the periodicity. We also didn't need any separate position to separate the isotopes, because as per the previous laws, periodic laws, it said that the periodic properties are the function of their atomic number, not atomic number, it's atomic mass. So you have to keep hydrogen, like keep all the isotopes separately in order to increasing number of their atomic mass, but it's not required right now. It's a very huge achievement for modern periodic table, and also it's easy to remember and reproduce. You can write it by your own, you can just learn it by your own, and it also correlates with the elements with its electronic configuration more clearly, and that also explains us how come the properties are similar for alkali metals, because they all have the similar kind of outermost electronic configuration, a very simpler one. Okay, so that is the explanation behind the periodicity, that the valence number of electrons are same for all the elements which are present in a group, and that makes all of these elements having similar properties, right? Well, I'll take you now, what is the demerit, that we still do not have where to put the hydrogen, because hydrogen has very common properties with alkali metals as well as halogens. So we do not know where to put the hydrogen. It's absolutely different from both of them also. It's similar to both of them also. Also, lanthanoids and actinoids could not be integrated in the main periodic table. That's a challenge we are facing. We have some more questions. What are called as the coinage metal, which is copper, gold, metal. These are the correct answer. The element with 57 will belong to what? You drive iron. I think it will be like S block, huh? Isn't it? Just subtract 30, just subtract 32. If I do 18, you subtract 32, it becomes 25, and 25 is the manganese. Manganese 25. So definitely it's a D block element. So use exactly the similar question, then you try it by your own. Finally, guys, we have come to the next part of this huge chapter. This part is called as the periodic properties. And before starting our periodic properties, let me give you an idea that what we have to deal with. There is a very important fundamental property that works when we go for the periodic properties, and this property, the fundamental property I'm talking about, is called as effective nuclear charge. But how effective nuclear charge is introduced? This effective nuclear charge has two terms. One of them is called as nuclear charge, another is called as electronic repulsion, also known as shielding constant. There's two things that we have to discuss right now. So whenever a positively charged nucleus is there with a positive Z is the number of Z is the number of protons, and E is the charge of a proton. It's a complete positive charge. One electron is revolving there, and there's a force of attraction that attracts this electron towards itself. This force of attraction is also equal to kq and q2 by r square, which is kz e square by r square. And there is one more force that works there, which is called as screening. Anyways, it's better that I draw a diagram and explain you the concept. So let us suppose there we have so this is a nucleus. There are electrons, 1 electron, 2 electron, 1, 2, 3, 4, 5, 6, 7 and 8, and there is 1 electron here. You all know what we are talking about. This is a sodium atom. This is a sodium atom. 11 is the atomic number. What we are experiencing over here, some repulsive force. What's happening here? This is a repulsive force. 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 Another repulsive force. So basically what we are observing, that because of these repulsions between the electrons, there is a overall repulsion. There is a overall repulsion which is working like this. There's an overall repulsion. This is called as sigma. This is called as the force of repulsion. Force of repulsion. We also have one more force which is towards the center, and this force is towards the center. This is a force of attraction. This is a force of attraction. So attraction and repulsion, both of them are working, but which is more dominating here? No doubt attractive only, because there is one more force that is working outwards called as the centrifugal force. Whenever a substance revolves in the circular dimension like this, it exerts a force called a centrifugal force, exerting outwards direction, and this force of attraction should be equals to that outward force as well as the repulsive force. So that's where the dominating force still is force of attraction. So what we see, that force of attraction is denoted by a term called as Z, which is atomic number, also called as the nuclear charge. And there is one more basically constant which is used in order to represent the force of repulsion. So force of repulsion, which is also represented by sigma, called as screening constant. And then comes the final version of considering both of them. We have Z effective, called as effective nuclear charge, which is equals to Z minus sigma. So this is something which is an important parameter here, called as effective nuclear charge. And effective nuclear charge is responsible to hold the electrons revolving in its shell, and this overall force is coming from the nucleus, which holds this electron parallelly revolving in the same field, same orbit, not letting it go outwards, and even dominating over the repulsive. Okay, and always remember that the force of attraction is always dominated than force of repulsion. So that's why, guys, now there is one thing that we know, which is Z, like hydrogen is 1, helium is 2, lithium is 3. Z is very easy to identify because it is also equals to the atomic number. It is also equals to atomic number. But how to identify the screening constant sigma? For this screening constant, we use a rule called as Slater's rule. What is this Slater rule? I'll explain very easily, quickly here. So let us suppose I am taking one example. In the example B, phosphorus with its atomic number 15. Right, everyone? So the very first thing that you need to do, write the electronic configuration in such a way, this way, that 1s, then it has 2s and 2p. So 1s2, 2s2, 2p6, 3s2 and 3p3. Okay, and so on. That's why I have to write. But 3p3, it's ended till here. So it's been asked that how to identify the value of sigma. So what you have to do is, for sigma is exactly representing you the force of repulsion. It's not a force. Similarly, Z, which is the atomic number, it's not a force of attraction, but it's a representative of the force of attraction. That force of attraction is directly proportional to Z somewhere. So Z is actually the representation of the attractional force. And similarly, sigma is also representing the repulsive force, but not exactly as the unit of force, but it is actually a symbol, a number which is creating, or which is basically differentiating between the Z and sigma. So sigma, what is sigma? Sigma can be identified using Slater rule. What does Slater rule say? Now I'll apply the Slater rule. Let me read it one by one. Ignore the electrons in the right hand side. So let us suppose if we are finding it for this electron. Okay, what electron should I take for? Let's say I'm talking about 3s electron, or let us suppose we are talking about 3p itself, 3p. So you don't need to consider anything which is right to it. Okay, let's say if we are asking it for 2p6, then we don't need to consider 3s and 3p. Probably I can take this example as well. Let us suppose this has been asked for 2p6 electron. Okay, how much is the sigma value? For this we have to find it for sigma. So write to it will be neglected. So we can also write that 3 plus 2 is 5 will be contributing as 0 plus. Next is 0.35 is added to the sigma for each electron in the same shell. You have to apply it for same shell. So how many electrons are there in the same shell? Second. Apart from this, there is like 6 here to here, 8. 8 minus 1 is 7 are there apart from 1. So 7 will contribute as 0.35 plus 4 electrons in NS or NP. Let's suppose there is something in NS and NP. Then what we have to do is electrons in the next lower shell will contribute as 0.85 and before that will be contributing 1. So 1 lesser than it having 2, so 2 into 0.85, and even if lesser shells were there, then we have to multiply it by 1. So how much does this come? This is 2.45 plus 17. This is comes as 19.45. This is sigma. And if you want to calculate out the Z effective, you also can do that. So how much is the Z effective? Yaar, how did we get it too much, yaar? Okay, well 1.7 is there actually. फिर बेचैनी काबे काटूं तुझे चैन जरा सा हो जाए. 4.15. The Z effective will be 15 minus 4.15 and the value comes up as 15 minus 4.14. It will be 10.85. So that's how you can find out the Z effective. Done, guys. But now if there is a D block element given to you or D subshell is given to you, for D subshell what we have to apply is this rule. I'm star marking it, that if any electron belongs to NF and ND and we have to put them again differently, okay, 4F, 4D, like that you have to arrange them. So this is saying that for all electrons below to it, all the electrons below to it in the energy contributes 1, and those who are in that shell, they will be contributing 0.35. Correct? And rest below to that will be contributing how much? 1 itself. So I'll give you one more example here. So here is the list, by the way. So let us suppose I'm taking an example for magnesium. Yeah, manganese, Mn with atomic number 25. We have to arrange first of all in a very simpler way, that 1s2, then 2s2, 2p6, then 3s2, 3p6, 4s2 and 3d10, and then 3d5, and then comes 4s2. That's how you have to arrange it. Okay, 3s, 3p. D and F are always kept separated with the this bracket. We have to take it. Now which electron you want me to fill it with? Tell me. So let's suppose I have to do it for valence shell, 4s. What do you think? No, D we have to do it. For D we should take it. Okay, 1 electron from here. Okay, so sigma I'm trying to calculate. What was the formula? Right to it will be contributing 0. So 2 into 0 plus the same one will be contributing 0.35. So how many? 5 are there. 4 will be doing it 0.3. So 4 into 0.35 plus all remaining coming left to the 8. All remaining in the left to it will be contributing how much? Let me see. All electron below it in energy will contribute 1. So 1, where can you find 1? 6 plus 2, 8. 8 plus 8, 16 plus 2, 18. So 18 into 1. That's how it will be coming up. I think it's coming too much, by the way. So how much is it? 4 पंजे 20, 2 12 और 2 14. So 1.40 plus 18 comes up as 19.40. 19 and 40 is the sigma. You can also find Z effective as Z minus sigma. So Z is 25 minus 19.40. So 5.6 is the Z effective. There you can check it. Fine guys, you can do it by your own now. Everything is pretty clear now. And this is the value of Z effective, but this data is for, so these are the values of, there all are the values of Z effective. These all are the values of Z effective for valence shell, the last shell, valence electron, the most last electron which is filled. Like that you have to do it. Okay, that is all your Slater's rule with you. And now let's see how does the variation of Z effective work. If we go in Z effective, predictable left to the right, Z increases by 1, sigma also increases, but overall Z effective increases. So this thing you have to keep in mind, that variation of Z effective in left to the right along the period increases, Z effective increases. Coming down the group, it sometimes it remains the same as well. You can take it as decreases, but no, it remains the same. So let's suppose if we are talking about along the group, so group 1 and 2, it remains the same constant from period 3 and onwards, and for other it increases up to period 4 and then remains constant. So we'll consider it as remaining constant only. Okay, this was an overall view, but don't be very serious about that part, because see, majorly if we talk about the JEE Main examination, we don't ask Slater's rule. Even in advance, if this rule is asked, there will be a proper I must say proper paragraph based question will be given, where the paragraph will be containing all of this information of Slater rule, then all it can be asked. But again, this is an important parameter that we have to take, like how generally it varies if we're talking about Z effective. So how does this Z effective work? So I'll write it like variation of Z effective in modern periodic table. In modern periodic table, how does the Z effective varies? So there are two things that we consider while considering the variation. The one thing is called as left to the right. This left to the right thing is called as across the period. Across the period. So if we move across the period, generally we see that Z increases, sigma also increases, but overall Z effective increases because Z is dominant over sigma, we all know. Similarly, if we go number 2, top to the bottom, and we say it as down the group. Down the group if we go. So if we go down the group, it's like Z increases, sigma increases as well, but Z effective remains same, almost same or constant. So take this thing in your mind, because this is something that is going to help us in our upcoming periodic properties. Let it be ionization energy, electron affinity, electronegativity. So these three things are the one, very importantly, even atomic size. And these 4 atomic properties we'll be discussing very soon, and that is going to be very helpful while we'll be going for the comparison of these properties. This is very much useful data. Z effective is going to affect us for every periodic property. So now let me take you to the first one. It's all done. Okay, always remember this part. If we talk about the shielding, so maximum shielding is done by ns orbitals being very because of its shape only. These are becoming very bigger in shape. Electrons are far from each other, do not repel each other. That's why D and F are said to have poor shielding. They are supposed to have the poor shielding. Always remember it. Boron atom has a screening due to. The boron atom has how many electrons? Boron atom has an electronic configuration of 1s2, 2s2, 2p1. So it has a shielding of s and s only, I guess, 1s and 2s. So 2 electrons of 1s and 2s each. All electron of K and L shell, all electron cannot have, because this is only one electron which we are having. Correct answer should be this, B. Z effective for 4s electron of manganese. I can do it by your own. Okay, you can also do it by your own. I can also explain it to you. So let's try this question. Oh, manganese Z equals to, so 1s2. How to write it? 1s2, 2s2 2p6, 3s2 3p6, 3d 5 and 4s2. This is the electronic configuration we have for manganese, and we are talking about this valence electron, by the way, 4s electron, 1 4s electron. Okay, so sigma will be how much? This will be contribute, 2 electrons are there, one will contribute by 0.35, plus the lower shell will be having a contribution of 0.85. So lower shell has how many electrons? Lower shell has how many electrons? 5 plus 8, 13. 13 multiplied by 0.85, plus lower to it will be 6 plus 2 plus 2, 10. So 10 multiplied by 1. Please count it, you will get your answer. How much does it come? 13 5 65 6 और 13 4, 13 तो 4, 11.06. How is it coming like this? 11.05 plus 0.35 plus 10. So 11 and 10 is 21. 21.40. I think 21.40 is the sigma, and Z effective will be how much? Z effective is what? Z minus sigma. Z minus sigma. Z minus sigma. Where can you write Z minus sigma? (25) is the atomic number. Sigma is 21.4. I think 3.6. 3.60 is the correct answer. A is correct. Next comes is atomic radii. Atomic radius, one of the very important property. This is called as your one of the what property we call it? Periodic property. So actually I want to start it from all the periodic properties and I'll take it to in one go. But before periodic properties, I want to take a small break from here, if you may allow. So what we are going to do is we are going to take a small break. Then we'll continue our periodic properties on the way. So let me just write it there so that you don't leave the class. Okay. So what next is in periodic properties are the next. So what you have to do is just stay tuned, and we are right now conducting a small break time. Just a 15-minute break time. Great. And those who haven't liked the session till now, guys, So now guys, let's take it and to finish the remaining topics. I have had my dinner, hopefully you too. Where were we? Yeah. So hi guys, hello Sohan, what's up? So guys, we have the next one is first periodic property called as the atomic radius. So you know what is the meaning of atomic radius? There is no direct method to find out the atomic radius, because we all say that electrons in an atom doesn't have a fixed position. We can only find the probability of finding of an electron in the nearby to the nucleus, but we cannot identify the exact position. That's why it cannot be said that what is the atomic radius. But yes, there are some techniques using that we can find out the differences, the distances between two nuclei, and between the distance can be divided by half if the same atoms are there, and that is how we can identify the atomic radius. So it's not a direct method to identification, but yes, relatively we can find out the atomic radii. So we have it's very difficult because the isolated atom doesn't exist. Number two, an isolated atom doesn't have a well-defined boundary, and a more accurate radius cannot be defined. But yes, we can identify the internuclear distance, and then we can calculate the radius using X-ray differentiation, X-ray diffraction technique, electron diffraction technique, and like that. So what I'm going to do is, let's say these are two similar atoms. Let's say this is sodium, this is also sodium, and between these two sodium connected to each other with a metallic bond, there is a distance that can be identified using X-ray diffraction technique. So the radius, which is actually this, so R will be equals to what? D by 2, that can be identified. That's what we'll be using as a finding of the distance. So guys, we'll be talking here about three type of radii. So this atomic radii, what we are talking about right now, atomic radii can be of three types broadly. Number one is called as covalent radius, RC. Number two is called as the metallic radius, and number three is called as van der Waals radius. So these three are kind of the radius that we have to discuss about. This will be Rm, this will become what? Rv. So if we talk about all of these three radii, covalent radius, what is the meaning of covalent? So the meaning of covalent is that if we attach two atoms together, let us say one of the atom is of hydrogen and the another atom is of chlorine, and no doubt these two will be, what I must say, overlapping to each other. Their region might be overlapping to each other because of the difference in the electronegativity. So here what we can say, that radius, the distance between these two, between this nucleus, this distance will be equals to the radius of hydrogen plus radius of chlorine, and these two radii are the covalent radius. Number two, we can find that if we have taken the complete hydrogen, this is somewhere lesser than that. This is lesser than that because D is the distance between internuclear. Okay, this is the distance between internuclear. Metallic radii, we'll be having metals with same shape, same size. Let us suppose these two are sodium metal atoms, and this is the difference between their nuclei. So the distance will be divided by 2, and that will become the radius of sodium will be equals to distance divided by 2. This is called as metallic radii. Coming to the van der Waals, let us suppose this is a helium atom, and a helium atom doesn't have any interaction toward the another helium atom directly via a chemical bond, but it is a van der Waals force of attraction acting between these two. And if I can find the distance between these two atoms, then the radius of helium can be determined as distance divided by 2. Now, even by looking at these three radii, if you closely look at all of these, you will realize, you will identify that the simple order of radius will become what? The radius of van der Waals is very, very bigger than radius of metallic, and the smallest will be radius of covalent. It's a general order. It's a general order of radii, right? For any metal, if you want to calculate the van der Waals, it will be largest in size and then followed by metallic and then followed by covalent. Let's have one question, by the way. We have a question here, everyone. In this question, the question is bond distance of carbon and fluorine in CF4, SF4 are respectively 1.33, 1.54. Carbon silicon bond length is 1.87. Then calculate the covalent radius of fluorine, ignoring the electronegativity difference. So it's simple. So what we'll be gonna do in carbon fluorine, we have radius of carbon plus radius of fluorine is equals to 1.33 angstrom. Then radius of silicon plus radius of fluorine is equals to 1.54 angstrom, and then finally we have carbon silicon. So radius of carbon plus radius of silicon, we also have 1.87 angstrom, right? It's a internuclear distance between all of these atoms. So it's more or less like a mathematical question. There are three equations and one is the unknown. The unknown part is fluorine over here that we have to find out. So how can we find out the fluorine? So do one thing, you can do one thing, you just add these two and then subtract that carbon and silicon will be subtracted from there. So just simply add these and then you will do what? Subtract this part. So what will be getting after that? Twice of the radius of fluorine will be equals to 1.33 plus 1.54 minus 1.87, and this whole will be divided by 2 and you will get your value. Okay, so I think B is correct. What do you think? B is correct. It's that simple. Then van der Waals, covalent, metallic. What's the basically relation I told you? Covalent, it is correct. Covalent is always lesser than van der Waals. Metallic is always lesser than van der Waals, and both A and B are correct. C is the correct answer. Now you try it by your own. Okay, let me check. Okay, so there we have the formula. I was just checking it, cross verifying it. So guys, always consider this thing in your mind. So let us say we are talking about the covalent radius here. If we talk about the covalent radius somewhere, and let's say there is an electronegativity difference. Okay, so there is one possibility. Then delta En is electronegativity gap. Electronegativity is something that we are going to discuss very soon, but before that we got to take this case under our observation. If delta electronegativity is negligible, and there is a third case where delta En, the electronegativity gap is huge, is not equals to 0. It's a significant gap is given. Let us suppose there is a given. Okay, so let's suppose there is no electronegativity gap, just like hydrogen and hydrogen atoms are connected. This is hydrogen, this is hydrogen. So simply the radius of hydrogen will be equals to the distance between hydrogen and hydrogen divided by 2. This is what we have to apply when covalent radius to be identified, electronegativity gap is 0. Another thing could be when there is a negligible electronegativity gap. Let us suppose we are taking we are taking hydrogen and another where we are taking iodine. So H and I do not have too much of the difference in the electronegativity. So what are we going to do? We'll simply say that radius of hydrogen plus radius of iodine will be equals to distance of hydrogen and iodide. It's like that we have to apply. But there is third case that we have to use, and the third case simply says that electronegativity gap is non-zero. So what is happening? Let's suppose this is hydrogen and this is, let's say, fluorine. Now you can see there is electronegativity gap. That's why their electron clouds have merged into each other, and this type of thing is called as overlapping, that we're gonna to understand in chemical bonding. Our next chapter, chemical bonding, will be understanding. This is the concept called as overlapping of the orbital. So that means these two have come even closer to each other. So in this way, how can we define the radius? So distance between the hydrogen and fluorine will be equals to covalent radius of hydrogen plus covalent radius of fluorine minus 0.09 times of delta of electronegativity. You have to find out the delta of electronegativity, will be given in the question, and then you have to apply it. So this is some scenario what we are facing right now in our previous question. So in the previous question, a compound AB, definitely there is an electronegativity gap over there of 1.9 and an atomic radius of these are given. So guys, distance will be identified as distance between AB will be that radius of A, covalent radius of B minus 0.09 multiplied by delta X, and that's how you are going to find it. What is this delta X? Delta of electronegativity. Just try it and you can find out the answer. 5.28 is the correct answer here. Now for every single periodic property, let it be atomic radii, let it be ionization energy, electron affinity, electronegativity, whatever it is, everywhere we'll try to figure out the variation in the periodic table. So how do we find out the variation? I told you once, number one, we take left to the right, we call it across the period. We call it across the period. So how are we going to go for across the period? If we go from left to the right, we know that Z effective increases. And I must tell you that the radius is inversely proportional to Z effective, because higher is the nuclear charge, lesser will be the radius. It's that simple. So how can we find out that Z effective increases and the radius keeps on decreases? Very simple. Okay. Number two, if we go from top to the bottom, okay, this is what I'm telling you. This is the general order. It happens generally, not exceptionally. Exceptionally, anything can happen like this. This has happened exceptionally. Okay, so this is a general trend. So if we go from top to the bottom, or we call it down the group, if we go down to the group, we know that Z effective remains same, Z effective remains constant, doesn't vary too much, but extra shell is added. If extra shell is added, guys, what will happen? If we go from 4s to 5s, size will increase, so radius keeps on increasing strictly, and that happens when generally. Exceptionally anything can happen, but yes, this is the order that we define as general order. So that's the general order in front of you. That's it. So now if we talk about the there is a, what's it by the way, okay, D block came. So एक एग्जाम्पल लेते हैं. Let's take an example from second period. If you take an example of second period, how many elements are there in second period, guys? In second period we see lithium. So lithium is bigger than beryllium, beryllium, boron, carbon, nitrogen, fluorine, and then neon is very large because this has a van der Waals radius. Getting me? Neon is the biggest. Similarly, if I take one more example of any group you can do, let's say first group we are talking about. So as I told you, in the group, every time we go left to the right, it decreases, so increases. So lithium is smaller than sodium, smaller than potassium, rubidium, cesium. So that's the size actually it follows. But if we talk about the group number 13, group number 13 has always been an exception to all of us. Right now we are in group number 13. So what happens in group number 13? The elements are boron, aluminium, gallium, indium, thallium. So if we talk about their order, so first of all boron, 5, 13, 13 plus 18, 31, 31 plus 18, 49, 49 plus 32, it's 81. So if you write down the electronic configuration of boron is helium 2s2 2p1. For aluminium, this is neon 3s2 3p1. For gallium, it will be argon 4s2 3d10 4p1. Now because of this extra D and its poor shielding, D has what? Poor shielding means lesser repulsion of electron, that's why more attraction. If there's more attraction, then size should what? Decrease. So we are going from boron to aluminium, the radius increases, but going from aluminium to gallium, radius decreases. Then again radius increases, again radius almost same. Why almost same? Let me show you why. So writing down its electronic configuration from indium, we have argon 5s2 4d10 5p1. For thallium, we have argon, not argon everywhere. This was krypton, xenon 6s2, then it is 5d10, and then it is 6p1. Now please identify all of them and get to the correct answer. So because of the poor shielding of D subshell, the size decreases, and again because of the poor, I didn't bring any F subshell there. Let me introduce F. 6s2 there, 6 minus 2 4f 14, 6 minus 1 5 d10, and 6p1. Now these are called as lanthanide. These are lanthanides and they cause what? Lanthanide contraction. Now what is the meaning of lanthanide contraction? I'll explain in one line, but yes, now we are pretty much clear that the overall order of radii will be the highest size. So okay, we have smallest boron, then comes gallium, then comes aluminium, then comes indium, and then comes thallium. So however, there's a it's almost similar, but a small gap will be there. However, it's a regular trend that thallium will be higher in size than indium. So it's a, I can say that's a small gap, like 2 picometer is the gap. So this is a very important part. Group 13 have always been a source of attraction, a very good source of attraction for JEE Mains and Advanced. It has been always asked, questions have been asked, guys. Questions have been asked upon this topic called as Group 13. So many questions have come till date. Now I'll take you to the next variation we see, which is in, okay, I'll explain the lanthanide contraction in separate, but first of all let's have a look how the size of D block is varying. Okay, so D and F block have always been a, what should I say, always very difficult to understand because of their very weird properties, and this happens mostly because of the unexceptional behavior of D and F subshells, which have a wider size, due to which with the increasing in the electrons, sometimes the repulsion decreases and atomic attraction or electronic attraction, electron and nuclear attraction increases, Z effective increases, and sometimes with the electron it gets on repelling also, so sigma also increases. So there's always a weird behavior of D and F subshell that I found, and due to which the size varies in a very random way. It's initially the size keeps on decreasing, then become constant, then increases. And for this logical explanation, we simply say that from going scandium, titanium, vanadium until there, the Z effective keeps on increasing, that's why size decreases, then it's constant, that's why size was constant, and from going to copper to zinc, the size again increases, and the reason behind the increment is the Z effective is decreasing. So you can check it out, guys. The decreases Z effective, that's why the size is decreasing. Sorry, the size decreases here, the radius is decreases because of the increasing effective nuclear charge, and then till here from manganese to nickel it is like almost constant and then increases. So this is increment is due to the R increases due to the higher nuclear charge, lower nuclear charge. Okay, this graph what you are seeing right now, this has been taken from the DNF block. Very good, DNF block, and from DNF block I've taken it. Also this is from what should I say, that this is actually showing you the all variation from left to the right for all, actually every single series, 3D series, 4D series, 5D series, like that. Okay, series 1 is your 3D series, series 2 is actually your 4D series, and this is your 5D series, and 5D and 6D have similar in sizes. Even 3D, even 4D and 3D are similar in sizes. So the series 1 only has some different values, and a similar way is seen in all of them. So we'll move forward and we'll take this thing next to the, so lowest size of this is being shown by 115 nickel here. The lowest highest size is of scandium, no doubt. Same applies over here. Yttrium has the maximum, lanthanum has the maximum, and minimum has been shown by, here we can see ruthenium has the lowest, and over here osmium, and these two have the similar sizes, iridium. Then if we talk about lanthanides, so earlier I was talking about lanthanide contraction, so let me talk about the lanthanides properly. Lanthanides, if we move from 50 atomic number of 58 to 71, 58 is your cerium. So this is actually lanthanum, this is cerium, cerium, promethium, you go to below until lutetium. Okay, so size is somehow very different, and what we see that europium has the highest size. This is of europium, so I'll star mark it because a remarkable number is there. So this is what happens, and that's what we have to learn about the F block, especially in 4F series called as lanthanide. There is one more point, we call it as lanthanide contraction. Okay, so I'll explain you what lanthanide contraction means. So 4D and 5D series almost have similar sizes. Why is it so? Because there comes the lanthanide in meanwhile. So lanthanide contraction has a vast impact, but what is it exactly, that I'll have to show you by considering all the lanthanide. But if you go for lanthanides, and if we take their sizes of radius of Ln3 positive ion, and Ln3 positive, and here is the Z. So what you'll observe that the size strictly decreases like this, strictly like this. Okay, so this is, let's say, lanthanum से पार एंड पम सम यू गॉड तब दिए हो यार तुम ये भी लो. So I've learned it like that. I don't know how you can do it, but I made my own way. I personally think that students should make their own way to learn down the mnemonics. I made it like La3 plus, so se par and pum sum you God तब दिए हो यार तुम ये भी लो. So that's how it is done. Okay guys, so the size keeps on decreasing, and that's why we say that the size of lanthanide keeps on decreasing strictly. This is called as lanthanide contraction. This is what we call as lanthanide contraction. This is the length-headed contraction. So now guys, let me finish this topic. And length-headed contraction has its own consequences, as we have seen that gallium, no, this is because of poor shielding of D, but thallium and indium are nearly same, but yes, again slightly greater. Radius of thallium is slightly greater than radius of indium. And for D block also we see that titanium, scandium, titanium is lesser, the size of titanium is lesser than this is actually your 3D series, but this is your 4D series and this is a 5D series. 4D and 5D size become equal, 4D and 5D. Why? Because of the insertion of the lanthanides meanwhile, because lanthanum belongs to the 5D series, and once the 5D series has been introduced, right after lanthanum comes the lanthanide, and then going to the hafnium, the size eventually decreases because of the poor shielding of F block, and that's what we call it as length-headed contraction. There's a question about the same thing which we have studied till now. So boron, gallium, aluminium, thallium, indium. No, it's not correct. It's boron, aluminium, gallium, boron, gallium, aluminium. This is correct, but again this is a slight change, slightly. Then we have factors affecting the ionic radii. If we talk about the ionic radii, so guys, let's suppose if we are talking about down the group we go, it keeps on increasing. If we go left to the right, it keeps on decreasing. But for isoelectronic species, let me explain you very important part of this session, that for isoelectronic species, whatever the isoelectronic species are there, the radius is inversely proportional to the number of protons or number of Z, effective atomic number. Like Z is the atomic number only, because Z is responsible for affecting nuclear charge, but number of electrons are the same, that means sigma will be same. So let's take an example. Let's suppose the example says, that's a good example. We have nitride, oxide, fluoride, sodium ion, magnesium ion, aluminium ion. Now if you have to compare the radius, how can you compare it? Check out their protons. So atomic number is equal to protons will be 7, 8, 9, 11, 12, 13. I have not taken neon because neon has a very different issue, which is van der Waals radii. So that is definitely going to be bigger than all of these. But I'm talking about only these ion representative elements. So electrons will be how much? 7 plus 3, 10, 8 plus 2, 10, 9 plus 1, 10, 11 minus 1, 10, 12 minus 2, 10, 13 minus 3, 10, 10, 10, 10, 10, 10. So now you can check out the size. That size keeps on decreasing. So nitride, this is the correct answer of ionic radii. That's you have to find out. Right. Chalo. Now I'll take you to the next questions. This all has been completed. There is a question, exactly the same example what I was explaining to you came in your JEE Main 2020. Same number of things are there. The correct answer should be nitride will be the maximum size. Nitride oxide fluoride. This is the correct answer. C. See, we just did it. Which of the following ionic radii is correct? So guys, always remember this part. For ions, if we talk about the ions, what has just happened here? Okay, sorry. So always remember one more thing, that if we talk about the ionic radii, higher is the positive charge, the radius keeps on decreasing. Okay, for the same atom. For same atom, it is directly proportional to the negative charge and inversely proportional to the positive charge. Very simple. So what is the meaning of this? Take an example, guys. Let's say we have iron, iron positive, iron 2 positive, iron 3 positive. What do you think? What is the size? Because we all know that electrons are getting decreased and protons are the same. So electron decrease, shielding will be decreased, attraction will increase. So this is the correct answer. This is the order of radius. Let's suppose there is an example, oxygen, oxide, oxide. This is peroxide, this is oxide. So this is the order of radius, directly proportional to the number of electron. Correct? And the rest I have told you about the isoelectronic species. So here also this was asked that which of the following is correct. So lithium has more size than beryllium, so this is incorrect. Oxygen 2- has than oxygen, this is correct, but nitride has the highest. I think this is correct. Oxygen, fluorine, neon. So neon is fine, but oxygen has bigger size than fluorine. And over here, so this is also incorrect. So oxide will be having highest, then fluoride is in this. I also have explained this example earlier. Next comes, which of the following order of atomic / ionic radius is not correct? We have to identify which of the following order is not correct. So fluorine, chlorine, bromine, iodine is correct. True. Which is correct? Yttrium, strontium, and rubidium. So yttrium 3 positive is there, and all of them have the same number of electrons. So if we talk about that, their protons or their Z is. You know about rubidium, potassium plus 18. Potassium is 19 plus 18 is 37. So 37, 38, 39. And but about their electrons will be plus 3, 39 plus 3, and this is 36. 36. So isoelectronic species have more number of protons, lesser is the size. So this is the incorrect order. Rest everything is fine. This all is because of the niobium is equals to deuterium, because of the 4D and 5D series have the nearly same size of because of the length-rate contraction. This is due to LC. I think radius is now completed. Sir, how much duration is left? We have a student here asking me how much duration is left. Yes, it's left actually, and it will probably take some 1 hour from here, because we have few more important properties left: ionization enthalpy or ionization potential, electron affinity, and then electronegativity. These 3 things we have to cover up. So anyways, we'll complete it ASAP. We have ionization enthalpy. What comes in your mind when you hear this term ionization enthalpy? It's nothing but just the amount of energy which is needed in order to eject out an electron, which is the most loosely bound electron of an isolated atom. What is the meaning of isolated atom? Means it should be in the gaseous state. It should not be having any attachment or interaction with the other atoms. So then how much amount of energy is required to eject out this electron to send it to infinity? So that's what we call it as the ionization enthalpy. And usually this process is endothermic, because what it requires is the first of all, it would require acceptance of energy, right? H nu, some photon with some suitable energy will go. So it's generally this process is ionization is endothermic process. Usually the process is endothermic in nature, but somewhere, let's suppose there is a cation and a cation wants to accept the electron. In that way, it can become negative also, energy may release. But one more thing you have to take into account, that whenever we go for successive ionization, the first electron which we were trying to bring out of an atom was easy to bring out. Let us suppose now it has acquired a positive charge, and now its Z effective has increased because of its higher number of protons than lesser number of electrons, and then even more amount of energy will be required. So whenever we go for the successive ionization, the ionization actually keep on increasing. So that's how it looks like. And there's one more thing that I want to tell you. That if there is a suitable gap, if there's a differentiable gap, huge gap, let us suppose the usual difference in the, whenever we talk about the kilojoule per mole, there will see the differences in terms of sometimes it could be double, tripled. Somewhere, let's say it's an increment of 200, 300, and randomly there's a huge gap of like 1000 kilojoule. So that huge gap is exactly telling us that this process, right from here, the ejection of electron is very difficult. The moment we have reached there, it has acquired a stable normal gas configuration that requires another 1000 joule to eject out the electron. So let's take an example. Sodium. These are actually the energies in terms of, I guess, kilojoule per mole. No, I don't know, man. But let's see how to identify this gap. 5 to 47, it's like 8 times gap, 8 times, and then 47 to 71, and this gap is nominal. So where did we find the huge gap? There we found the huge gap. This is the huge gap. There is a huge gap. What is this huge gap telling us? That one electron can be ejected out, second cannot be. That means it has a valency of 1. If we are gonna to remove 2 electrons, then it will take too much of the amount of energy. 11 to 26, 26 to 47, 47 to 77, and then a randomly a very big amount of energy. There's a huge gap. So how many electrons were ejected? 4 electrons were ejected. That means 4 electrons were in the valence shell. Fifth one we couldn't, because fifth one required a higher amount of energy, because it already had acquired a noble gas configuration. That shell was now empty. The valence shell was now empty. 5 to 18, 18 to 20, 20. Now there's a huge gap. Because of this huge gap, we can tell that 3 electrons can be removed, and then valence electron will become 3. Let's see a question. Which of the following alkali metal? Which of the following is an alkali? You know alkali metal? Alkali metals have a configuration of NS1. So if they have NS1 configuration, only 1 electron can be removed. The second one will be removed with a very difficulty. Required a huge amount of energy. So first it could be nominal, second it should be highest. Where can you find the largest gap? I think the largest gap is over here. C is the correct answer. Now. We have another question. Let's first of all understand the general variation or the trend in periodic table. So what is the variation of ionization enthalpy? Variation of ionization enthalpy, and we have to understand this variation in modern periodic table. variation of ionization enthalpy in modern periodic table. So how can we do that? Variation of ionization enthalpy in modern periodic table. First of all, we'll go from left to the right across the period. So whenever we go across the period, Z effective increases. If Z effective increases, then radius, okay, not radius, yes, radius decreases, and then ionization enthalpy increases. So first of all, we must know that ionization enthalpy is the amount of energy required to eject out an electron from the gaseous state, isolated atom. So it must increase with Z effective, so it is directly proportional to Z effective. Higher is the amount of energy required if the Z effective is higher. And also ionization enthalpy is inversely proportional to the radius, because higher is the radius, the electron will be far from the nucleus and it will require lesser amount of energy to eject it out. So that's how it works. We have left to the right variation, then we have top to the bottom. Let us suppose we are going from top to the bottom, then what happens? Top to the bottom, we have Z effective as constant. Z effective is nearly constant. Radius keeps on increasing. If the radius increases, then we all know that ionization enthalpy should go for decreases. So that is the ionization enthalpy and its variation. Let me take you to one example. Let's suppose we are talking about the but yes, it's not every time will happening, and whenever we are writing this, but exceptions will be there. Exceptions at the rate whenever there is a stable configuration seen, whenever there is a higher stable configuration can be seen, then we can say that this has to be changed. Okay, what is the meaning of that? Whenever there is a variation, let's suppose if we are talking about ionization enthalpy increases, but exception will be seen at the rate stable configuration. But the meaning of stable configuration is fully filled configuration, singly filled configuration, like that. Okay, so taking to you one example, second period element. You all know about second period element. Second period element has lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then comes neon. So you better try it by your own. Try to write down its ionization enthalpy order, and then I'll explain it to you. Okay. So let's see who has submitted with the correct answer, and seems like nobody. Not a problem, everyone. So we'll try to figure out what's been given and how it has to be done, how it is done. So first of all, let us take their atomic number. Lithium is 3, then 4, 5, 6, 7, 8, 9, and 10. So if we move from left to the right, you will see that electronic configuration works like 2s1, 2s2, 2p1, 2s2, 2p2, 2p3, 2p4, 2p5, and 2p6. So now if I want to ask you that where can you find these stable configurations, So this is S2, completely filled S subshell. Then P3, half filled P subshell. And P6, fully filled subshell. So there will face some change, some shift. So oxygen will have lesser than nitrogen, so this will be coming jumped from its position to oxygen, and then boron will be having lesser than beryllium. They are situated one position. This doesn't have any situation, and neon being the noble atom will have the highest ionization enthalpy. So neon has the very high ionization energy, followed by fluorine. Then nitrogen must come before oxygen. This is what I meant to say by this arrow. Then from there carbon. Then instead of beryllium or instead of boron, we'll come to beryllium. Then comes boron. Then comes lithium. And this is the order of IE1, first ionization enthalpy. That is the order of first ionization enthalpy. Got it, guys? Like that, okay? So you can try the same thing over here. Let us suppose if I give you an example of third period. Let us talk about all the elements of third period. What elements are there? We have sodium, we have magnesium, aluminium, silicon, phosphorus, then we have sulfur, then comes chlorine, and then argon. Talking about their electronic configuration, it has 3s1, 3s2, 3s2, 3p1, 3p2, 3p3, P4, P5 and P6. We have completely stable configuration, completely fully filled configuration of argon, phosphorus, magnesium. Now considering all of these three, they will be moved by one position like this, and this has always the bestest or the highest ionization enthalpy, argon, then followed by chlorine, then comes phosphorus before sulfur, then we have silicon, then we have magnesium first, and then comes aluminium, and then last comes the sodium. Sodium has the lowest ionization enthalpy out of them all. This is the order of IE1. Now guys, as if you all remember, even in atomic radii I was discussing about group 13, which had very weird, very different kind of order here also. But there is, I can give you one biggest trick to know about the group 13 ionization enthalpy. Okay, so let me first write them. This is first ionization enthalpy which we have to talking about. So guys, from here, so guys, in next 30 seconds I'll explain you how to learn the first ionization enthalpy order for group 13 elements. So group 13 elements are boron, aluminium, gallium, indium, thallium, and you need to remember this WWE wala logo. This logo has the correct answer. This W, this twisted W has the correct answer. Okay, so this is your boron, this is aluminium, this is gallium, this is indium, and this is thallium. So the correct order of first ionization enthalpy will become what? Boron has the highest, followed by thallium, followed by gallium, followed by aluminium, and the lowest is possessed by indium. And this question was asked in your JEE Main 2025 related to indium. Okay, so now you want to know why this order has been followed. So it is simple, guys. So boron, aluminium, gallium, indium, thallium. Boron to aluminium, the ionization enthalpy decreases. It usually should be. It increases due to poor shielding of D subshell or d orbitals. Then going from indium, gallium to indium, see gallium to indium, it again decreases, which is right, which is no very weird thing. And then indium to indium, this is increasing. Why does it increases? This is due to lanthanide contraction. Because of the lanthanide contraction, you know what is lanthanide contraction? Exceptional reduction in the size of lanthanide, that causes exceptional reduction in the size causes what? Higher Z effective, and higher Z effective causes you what? Because of the higher Z effective, ionization enthalpy increases. So that was group 13. Next is, we are now talking about the D block. So if we come to D block, the more specifically we have to talk about 3D series. 3D series is the most common thing that we can talk about. 4D and 5D are pretty much complicated. So the general trend says that there is a slight increase due to the increase in Z effective values, and from coming to 631 to 656 there is a slight increase you can see. Then it's a weirdish order which you can see, very weirdish. However, it's keep on increasing from going left to the right, but there is somewhere which we can find sudden jumps. Sudden jumps is from copper to zinc, because this is because of the most stable fully filled stable configuration. So we were quietly talking about the D series, and we know that ionization in the D series is approximately equals to the 4D series due to poor shielding, and 4D and 5D we have a huge gap because 5D series is higher. Why is it so? Because of the length contraction. Usually we see that from 3D to 4D if we go, it decreases, but it is similar because of the poor shielding, but somewhat lesser only. You can check it out, you get somewhat lesser only. But now when we go to the 4D to 5D, lanthanides come in between, and lanthanides have poor shielding, higher Z effective, causes higher ionization enthalpy of 5D series. Okay, and there's an exception, that scandium, yttrium and lanthanum. Okay, so no lanthanide contraction in lanthanum, so that's why scandium has the highest, then yttrium, then lanthanum. This is not exception, this is actually normally it is there. It's not exception, this is the normal way of trend. So now applications of ionization energy. Low ionization enthalpy of indicate its more electropositive character. It can easily lose the electron, it has higher reducing energy, reducing agent. It can become good reducing agent, because something which can lose electron easily can become an oxidizing agent. As I told you, can become it's undergoing self oxidation. It's a good reducing agent. This is something I taught you in the previous class of redox reaction, where I taught you that a reducing agent itself undergoes oxidation. So that's what this atom will be doing. There is a question that first ionization potential of beryllium and boron. So we all know that beryllium has electronic configuration of 2s2 2p1, and this boron has a this has a 2s2 and this has a 2p1, 2s2 2p1. So easily can be removed from this. So this will be having lesser value, and the first one will be having higher value. So 9.32, 8.39 is the correct answer. First is higher, second is lesser. Which electronic configuration has an abnormally huge difference between the second and third ionization? So second and third gap, that means valence electrons will be how many? Valence electrons are 2. Where can you find 2 valence electrons? Over here. And right after that, stable configuration should come. Which of the following is the correct order of ionization enthalpy? So guys, wherever the positive charge increases on an atom, Z effective increases, ionization enthalpy will also be increasing, because there's already one electron has been removed. It will take more amount of energy to remove. So this is true. This is incorrect. Carbon, beryllium, we move from left to the right. This is also true. Boron has lesser ionization enthalpy than beryllium, but carbon is higher. Then boron has higher than beryllium. This is also false. So the correct answer should be that first and 3 are correct. First and 3 are in the C option. Now you will try this question by your own homework, and I'll bring some very beautiful questions. Okay, this is also one of the good question, came in JEE Main 2020. I can explain this question. So beryllium has a smaller atomic radius than comparing to the magnesium. Beryllium has smaller radius. This is true because size keeps on increasing going down the group. Beryllium has high ionization enthalpy than aluminium. So beryllium has 2s2. I may have, and aluminium has 3p1. So this is also, I guess, true, and they are like similar. I guess they have similar amount of energy, but yes, beryllium must have higher because lesser number of shell is there, no more amount of energy will be needed. And charge oblique radius for beryllium is greater than that of aluminum, which is actually similar also. And both beryllium and aluminum form covalent compound. No. So this has been asked, how many of them are correct one? So first, second and fourth are correct, I guess. No. I think first, second and third are correct. And this is also true. False. Beryllium forms BeCl2. Highly covalent, but AlCl3 is ionic. This is something which has been like based upon what should I say? We call it Fajan's rule, and some other things are there which are related to chemical bonding. So let's not touch this concept as of now, but later on we'll come to this concept and we'll explain you how is this been decided. But yeah, the correct answer is first, second and fourth. So which is now a blunder to all of us. Now we all have attempted incorrectly. First, second were already true, but charge of radius ratio is greater then that is actually false statement. Why is it so? That I can explain. Because whenever charge and size are two things, so beryllium forms 2 positive and aluminium forms 3 positive. Sizes are quite nearby, but it's more or less about the charge. So more charge density is with Al3 plus, not this charge density like I'm talking about Q by radius. So I think that is the reason fourth has been taken. But again, it's not completely based upon the concept which you are right now studying, but it's a mix of the concepts, and some of the concepts are taken from chemical bonding as well, which I'll be going to bring in my next sessions of the chemical bonding. So we can pick the answer as A as of now, and we'll move forward to the next question. In fact, our next property called as electron gain enthalpy, very simpler and very easy concept, because if you have gone through ionization enthalpy, then you can easily relate with this also. Again, just like ionization enthalpy, electron gain enthalpy is also defined for an isolated atom, that if an atom is present in its combined state, you have to first break it, you have to bring the atom in its gaseous state, and then only we can add an electron. Adding an extra electron is called as electron gain enthalpy. So whatever the amount of energy usually that releases in this process called as the, or the change of enthalpy that takes place, change in the amount of energy that takes place is called as the electron gain enthalpy. But sometimes, usually it's a exothermic process. Why is it an exothermic process? Because it requires, like, energy is released whenever an electron comes. We all know that the energy of a shell given by Bohr's formula in atomic structure was negative 13.6 z square by n square. The negative value comes. So whenever an electron extra comes, this amount of energy is released. Usually this happens. But whenever we are adding an electron to a stable configuration or already existing anion, then this process becomes endothermic in nature, reverse. So that's what we'll see. And let's see. So electron affinity of an electron is greater than that of the second one, and yes, first electron gain energy is released in lesser amount, but when electron extra is added to an anion, energy is required even higher amount. So that's what you can see, that delta H of Eg1 is always in magnitude lesser than delta H of Eg2, because Eg1 can be delta H Eg1 usually can be less than 0, but delta H Eg2 will be greater than 0 always, every time, for the same atom. So there's a variation you can see of electron affinity. No doubt we are not supposed to learn down these values, but yeah, I can explain it to you. So I'll explain you now the variation. variation of electron affinity. But before that, I must explain you the difference of electron gain enthalpy versus electron affinity. First of all, we must understand the difference of electron gain enthalpy, electron affinity. So electron gain enthalpy, how do we identify electron gain enthalpy? This is actually represented as delta GEG1, and this has been treated as EA. So guys, this represents an absolute amount of energy it represents an absolute amount of energy released when 1 mole of electrons added, anyways, when added to this that we already know. So this is more or less the amount of energy released oblique gained in the process of electron gain. But electron affinity, it's a relative term, it's just a tendency to accept an electron. So what is the combination or the relation between these two? That see, if something has a tendency to accept the electron, then electron affinity will be positive. In that way, energy will be released, so electron gain enthalpy will come in negative. So how come these two are related? These are related as like mode of electron gain enthalpy, or delta H electron gain enthalpy 1 negative will be equals to the electron affinity. So this is the first thing that we have to accept. Okay, so take an example. Let's say we have chlorine. The electron gain enthalpy of chlorine be EGE1. First electron gain enthalpy means first electron when it is accepting, forming chloride ion. Let's say this is minus 540 kilojoule per mole. Let's say, just taking an example. So its electron affinity 1 of chlorine. Like, what is the tendency of chlorine to accept this with no unit? It is just 540 plus. Okay. But now I'll give you one more example. So let's say negative of delta H1. So let's take one more example. So whenever we will be having electron gain enthalpy 1 of argon, let's say we are talking about, and let's say it is a positive 500 kilojoule per mole. Argon doesn't want to accept an electron, it's already stable. Then electron affinity 1 of argon will be equals to, simply we'll write it 0. Okay, negative of 500, don't make it negative, it's simple, the tendency, so tendency will become 0. So either it is positive or it is 0. This is what about electron affinity. But what about electronegativity? Electron gain enthalpy, this is an absolute value, whether it is required or released, so that you have to take as an energy value. But affinity you have to take only up to the tendency to accept or lost, tendency to accept the electron. So that's how it's given all of the data to us, and it also works in the similar way. So variation we were talking about the variation. How do we find out the variation of electron affinity? Now I can totally talk about the electron affinity rather than talking about the electron gain enthalpy. So now we'll talk about the electron affinity, because electron affinity is easy to understand. Electron gain enthalpy was not too easy to understand, because the amount of energy was released there and it's taken in negative. So then the question will also become difficult, like more negative, less negative. No, it's better to keep higher electron affinity, lesser electron affinity. So variation of electron affinity. So first thing, electron affinity is directly proportional to Z effective, because it's the amount of energy required. Like electron affinity is a tendency to accept the electron, and electron will come to, if the higher is the Z effective over there, higher is the radius, far will be the electron from the nucleus, and then it will be lesser amount of energy or lesser tendency of the electron to accept. Lesser tendency will be there. So now considering these two, if we go from left to the right, across the period, then we know that Z effective increases, radius decreases, so that's why electron affinity will increase. If we go from top to the bottom, then Z effective is constant, radius increases, and that is why electron affinity decreases. But again, you will find some exceptions at the rate stable configurations. So whenever there will be some stable configuration, there will be finding the exception. Okay, let me take you to one example, such example. So let's see the example. Let's say we are talking about all the elements of second period. So what elements are there in second period? Second period has lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then neon. Then the electronic configuration will be 2s1, 2s2, 2p1, P2, P3, P4, P5 and P6. So among them the most stable configurations are neon, we have nitrogen, and we also have beryllium. So definitely guys, these will be having the lowest electron affinity, so we have to keep them separated. That neon will be having 0, then from neon higher will be of nitrogen, and then of beryllium, because these three are supposed to have 0 electron affinity, right? 0 electron affinity. But this will be in fact what should I call it, endothermic process. So then the order is pretty simple: lithium, boron, carbon, oxygen, fluorine. This is the order of electron affinity. The same thing you can apply for third period also. Similar concept will be applied. Talking about the electron affinity for group wise, if we take an example, so let us suppose lithium, sodium, potassium, rubidium and cesium. So as the size increases, the amount of energy, the tendency towards electron will be decreasing. So this is the order of EA1, first electron affinity. But you have to note down one thing. Whenever we talk about the groups, we have to note down one thing. There is a note, and this is like from group 13, 14, 15, 16 and 17. This is for all of them. Always remember that EA1 for first element, EA1 for second period element will always be lesser than the EA1 of third period element. And I want to check this data also, whether this works in 13th also. Boron element increasing, everywhere it is increasing. So it's very simple that you have to learn that group 13, 14, 15, 16, but not happens in the case of, it doesn't work in the case of alkali metals, but yes, it works in the case of just p block elements. Okay, why is it so? Due to very small size of second period elements repelling extra electron due to high electron density. So that's the reason for which you will find, it's a homework for all of you, that you got to find out the order for group 16, group 15, group 16 and then group 17. For all of them we have to find out the correct order. Group 15 we have phosphorus has the highest, 17 we have chlorine, then fluorine, then bromine, then iodine. Check out this guys, check out, this is the difference. For 16, oxygen is the lowest one, so it will be sulfur, selenium, tellurium, polonium, and then come oxygen. This is the order of E1. And for this I have to check it from the values given. Nitrogen is less than 0 electron affinity, and this keeps on increasing, but it's a random, basically random, so not so easy. A maximum. So this is a very random basically, and doesn't work like this. Bismuth unnecessarily has the highest. Antimony has the highest. Nitrogen is the lowest, like that. This is the order, very weird one. So that's you have to learn, by the way, but that's it. This is the order of E1. So that's it, everyone. That's it for electron affinity. We'll try to solve some question and then we'll wind up. So among the halogens, the correct order of amount of energy, fluorine, chlorine, bromine, iodine. Electron gain we have to find out the amount of energy in the magnitude we are talking about. So chlorine will be having the highest, then fluorine, bromine, and iodine. C is correct answer. So this is a homework, you try by your own. So the final, last and final, yeah, atakra ye wire yaar. We have the last final one. This is your electronegativity, final periodic property called as electronegativity. So what is electronegativity? How is it calculated? First of all, electronegativity is a hypothetical concept. It's not seen in practicality. It's not a real concept. It's all hypothetical, because what happens, let us suppose there are two things. One of them is hydrogen, another one is chlorine. And let us suppose there is a covalent bond between these two. A covalent bond is formed by accepting, like by mutually sharing the electrons. Hydrogen shares one, chlorine shares one. But what happens that hydrogen being less electronegative, or it is lesser electronegative than chlorine, and chlorine being more electronegative than hydrogen, tries to acquire its shared pair of electrons. So it is always, electronegativity is always considered in bonding stage. So chlorine will try to abstract the electron from itself, so that chlorine acquires a partial negative charge, hydrogen acquires a partial positive charge. This is the concept of electronegativity, that the shared pair of electron wants to come closer to that atom which has higher Z effective, is as simple as that, and higher electronegativity especially. So that's it. Okay, mathematically there are two things, two scale. One of them is called as Mulliken scale, but our real scale that we count it upon is called as Pauling scale, more important one. But Mulliken scale is very simple, that electron affinity plus ionization potential. So this is not ionization enthalpy, this is actually ionization potential taken in electron volt per atom, and both of the energies are taken in electron volt per atoms only. So divided by 2 we have to do, but it's a quite complex in calculation and not very accurate value we get. So that's why this is not too much hard and fast followed, but what is followed is called as Pauling's scale of electronegativity. Electronegativity is pretty simple, that whenever two atoms are bonded together, the higher electronegative element will try to accept shared pair of electron pair towards itself. This is called as electronegativity. How we are deciding that that chlorine is more electronegative? Because chlorine tried to accept the electron pair toward itself. And also there is one more thing, that it's always defined in the state of combined state, not for an isolated atom, we can say. Okay, so how can you identify? The Pauling basically did one, Pauling assigned highest electronegativity of fluorine equals to 4. He assigned fluorine as the highest electronegative element in modern periodic table, and he also assigned the electronegativity as 4. and using this 4 he compared for all of others. So this EA, this is actually X is actually electronegativity of A minus B, and one of them can be fluorine, can be defined as root of 0.0 this no 0.07 this under root of electron energy of this minus another root of this. This is the formula. Same applies over here. So both of the formulas are exactly the same. The only difference is of this number. This EAB is called as the practical or actual bond energy, and this value of under root of EAA into EBB is called as the theoretical bond energy. So when the energies are expressed in kilocalories per mole, you've got to take this formula. In kilojoule per mole, we will take this formula of identification of the electronegativity gap. So let me just rethink what the formulas are. 0.1017 when the energy is on kilojoule per mole. So let's suppose we have to convert it in kilojoule. 0.20 will be out. Okay. That is why this formula is coming like this. So energy in joule is nearly 4.2 times of energy in oppositely I have written energy in calorie is equals to energy in joule oppositely I have written it. Energy in calorie multiplied by 4.2 will be energy in joules. So definitely the magnitude will be higher in the terms of calorie there, okay? But ultimately x minus x will come same, okay? We'll move forward, not so much required. Believe me, I've been teaching from past 10 years. I have not seen a single question coming on that equation. So just move forward. That's not even in our syllabus. No need to total and down there, but just take an idea and just move forward. That's it. So we have, if the question comes as a paragraph based, then a proper paragraph will be given related to these formula. And okay. Yes guys, so where were we? We have relationship between the Pauling and Mulliken scale. It's roughly calculation is that Mulliken scale had higher value than Pauling scale, and Pauling scale when multiplied by 2.8 gives you the electronegativity on Mulliken scale. This X, what you see, this is not X, this is chi, Greek letter chi, and this is actually a symbol of electronegativity. So what the electronegativity depends upon? Oxidation state. Higher is the oxidation state, higher will be the electronegativity, because electronegativity is directly proportional to Z effective, and electronegativity is also inversely proportional to the radius. So that's what works for everywhere. Hybridization, you do not know about hybridization, but higher is the percentage S character, closer will be the electron toward the nucleus, and higher will be its electronegativity. You do not know, just forget it. We'll come to the topic and then we'll later on explain it. So in a period, Z effective increases, so electronegativity increases, down the group it decreases. It's a very simpler basically way to understand. Cesium, that's why has the lowest, and fluorine has the highest. So that's a value that we have to learn about. Some important values we have to learn, guys. Please learn it for, and the values are already given there. I'll give you the task that fluorine, chlorine, bromine, iodine. This is what you have to learn. Then hydrogen, phosphorus, carbon, sulfur, oxygen, chlorine. These are the elements for which we should learn it like on the tips. Okay, I forgot nitrogen. That's it. Which of the following is most electronegative? No need to explain here. On non-metal is nowhere. Top more hydrogen. The rest are the metals. Then applications of electronegativity. How applications of electronegativity will work? So ionic character in a bond can be identified. Ionic character in a bond can be identified using this. The formula is this, called as the Henny-Smith equation. Okay, it's written there, Henny-Smith equation. I haven't seen any question on this formula also, but it's an important formula. We must take this thing in our mind, that 16 of delta x plus 3.5 delta x square. There's a question that you can do by your own. The answer will be 91%. Then prediction of nature of bond. Okay, I'll sit now somewhere and then we'll explain the remaining part of this chapter. So now the question simply says that, not it's a question, it's just very simple, that if delta, see this is the equation, if you put the delta x there and you try to find out where can you get the ionic character or covalent character. So if delta x is more than 1.7, then it will be purely ionic, mostly ionic, lesser covalent character. No bond is purely ionic, no bond is purely covalent in nature. This is what chemical bonding says, but again 50% ionic and 50% covalent in case of 1.7. If it is less than this, then more covalent, less ionic will be there. Then next question is so delta, it's very simple yaar, matlab applications is like bond length is inversely proportional to the delta En. Higher is the difference in electronegativity, lesser will be the bond length, and higher is the bond energy. So anyways, this is we'll cover in there, we'll be covering it there in our chemical bonding. Then we have some oxides there. So guys, we know that acidic oxide, higher is the delta x, then higher is the acidic strength increasing. So it's very simple that metallic oxides are basic in nature, ionic oxides, non-metallic oxides are acidic in nature, and meanwhile whenever the amphoteric oxides are also there, which are either by the metalloids oxides are there or somewhere else you can find it. But anyways, there is some set of amphoteric oxides that I can tell you where you can find the amphoteric oxides, which can behave as both acidic as well as basic oxide. These are called as amphoteric oxides. So amphoteric oxides are these are the element whose oxides are amphoteric in nature. So this is basin, gall, jeep, per. Basin, gall, jeep, per. So their oxides like beryllium oxide, SNO, SNO2, Ga2O3, Al2O3, ZNO, PbO, PbO2. These all are amphoteric in nature. Then we have some neutral oxides. Neutral oxides are the one which are neither acidic nor basic. So amphoteric are the one which can act as both acidic and basic. They can accept H positive, they can accept OH negative. But neutral are neither acidic nor basic. Neither acidic nor basic. So the correct example of neutral oxide could be carbon monoxide, nitric oxide, nitrous oxide. That's it. Rest nitrogen oxides, non-metallic oxides are acidic in nature, and metallic oxides are basic in nature. Okay. Done. So when we move left to the right, acidic strength increases, basic strength decreases. Top to the bottom, basic strength increases, mostly are the basic. So this is something that you got to take into account. Higher is the oxidation state, acidic strength also increases. Why is it so? That I can explain you, because whenever the higher oxidation state is there, the difference is, or we can say more stable ion will be formed there after losing H positive. So they are more or less like acidic in nature. Lesser oxidation state, higher is the oxidation state, and higher will be the acidic strength is there. So you just read it out once by your own, guys, and I think that's it. We'll try some solving questions. This is the actually explanation based upon electronegativity for acidic and basic properties of the hydroxides. That's it, yeah. So these are some set of questions. Please try them, and then we'll connect very soon in our next class. That's it for the day. And now I feel tired and I'm quitting from here. And yeah, we have Ashish Kankane. Ashish is asking me something. Yeah, Ashish, I can hear you. Tell me what you want to say, Ashish. Guys, you can ask me if there is any question. If anybody has any question, please let me know. I can reply you. I can give you the answer. I can resolve your doubts. But right after from here, we'll wind up the session. We'll all leaving from here.